Good morning. Just in time for Kevin to arrive. Great. Nice to see you all back. Start with Ilyes Batatia, who is a famous maker of mace, and let's see what he has to tell us.
Thank you much for all the organizer for inviting me and everyone here in the audience. So I'm Ilyes. I'm a student in Gabor Chinese group in Cambridge, and I'm going to talk about foundation models for chemistry, but I'm going to start a bit with some theory on mace because I thought, because this is a lecture, I will start a bit from the basic. I know that Nicolas said some of these things yesterday, but I mean, it's always nice to repeat. So, okay. So this is not working anymore, but usual. So some introduction. Really, what at a high level, what we are trying to do is find a way to scale up computational chemistry. So this is a plot that is classifying some of the methods to do computational chemistry simulations, and the axes are the size of the simulation in the number of atoms and sort of accuracy, which is very hand wavy. But you can think about, like, if you compute some observables, what kind of accuracy you can expect on them. And here on top, you have the quantum chemistry methods, which are basically solving the Schrödinger equation directly with the least amount of approximations, and you get something that is very close to it. So you can think of full CI for the very smallest systems, or coupled cluster, Monte Carlo methods. Monte Carlo. Here you have the quantum Monte Carlo, which is a bit more accurate, and here the DFT, which is not so accurate, but still accurate enough to be useful, and it can go for from 100 to 1,000 atoms if you push it very far. So you can still do quite a lot of system, but it's still quite expensive. So at the very top, you have the most grains methods, which basically can simulate billions of atoms. And you have also the classical force fields. And in a lot of situations, when you want to understand physical systems, you need both the size and the accuracy. So you cannot just go on the stressed line here where you scale up the atoms, but you lose accuracy. You need to be able to go in a sort of horizontal direction there to get meaningful answers. And this is the promise of machine learning force fields, which basically try to learn basically DFT in most cases, but scale up by a factor of 100 to a million in terms of speed or link. And having something that is basically doing a 10,000 atom for the accuracy of DFT is grown for a lot of application, and it's basically the sweet spot that most ML force fields are here at the moment. Here you have a plot of all the computational resources used in the latest CPU cluster in the UK, which is called Archer. And you see all of the orange lines, and also here the sort of purple lines. Of these are things that are using solving the Schrödinger equation. So basically, about 60 to 70% of the annual budget the national cluster in the UK is just solving the Schrödinger equation with different level of approximations. And so this is showing how important it is for us to be able to solve this equation fast. And the funny thing is that in most of these computational usage in this cluster, most of the Schrödinger equation is not used at all. So if you remember a bit of the undergrad quantum mechanics, and this is the Schrödinger equation, and when you solve it, what you get is the solution is a wave function. And the wave function is a very high-dimensional object. It's something that scales exponentially with the size of the number of electrons, and it's a very complex thing. It's very expensive to compute. And what you do in reality with most of these things is you do molecular dynamics. And in molecular dynamics, you just forget about the wave function that you have spent so much time computing. You throw it to the bin, and then you just keep the forces, which are basically just the sort of classical average of the wave function that just tells you classically how the atoms move. So done all of this work, solve the super complex differential equation just to get something that is actually quite low dimensional. So really it feels like there should be a shortcut, at least in system, a way to just shortcut the wave function and just go from just the position directly to the forces. And actually, this is exactly what we do when we do this machine learning force field. We just learn a function that is a function of all the position of the atoms to just a scalar, which is the energy, and then you take the derivative of that and the forces. And by directly doing this mapping, you basically coarse grain all of the complexity of the Schrödinger equation. All of the electrons disappear. So you have no electrons here. Obviously, you lose something because electrons are real. So there is something that you lose. But in a lot of cases, you don't really need the full wave function to get the physics right. And by doing this shortcut, you basically can scale up now to a much bigger system. So here you have a simple reaction. And here this is like a full mini battery simulation for nanoseconds. This you wouldn't be able to do at this rate if you haven't done this coarse graining of the electrons. So really that's the most important step in modeling that we are doing with this ML force field. And so as I said, all ML force field, I will say force field or potential, like they are the same thing to me, but all of them basically learn the energy as a function of the position and also the species. So basically, if it's hydrogen, oxygen, and it's actually quite important because, okay, you cannot forget about all the electrons. So basically, putting the species gives you a sense of all of the electronic structure of each atom, but at a very grain level. And one big approximation that most models do today, or at least the most successful, is an assumption of locality. So if you have an atom I, its energy is basically only a function of its neighborhood, which is basically some atoms that are some distance away from the central atom I. And the total energy is also partitioned into a sum of site energies. And this is very important because it's a huge modeling choice, and it's in most cases not a big deal in terms of approximation. So it works quite well, and it allows you two things that are very important. First, it means that usually all of these methods are linearly scaling with the number of atoms, so you can really go to larger system. And the other thing is that it allows you to learn a function that is a sort of composition function, therefore you can learn on small systems and expect to extrapolate to larger systems. And this is very important. The promise of these models are to basically train on DFT or higher level of theories, where you can only do small systems, and then at test time, running on larger systems. The locality is a strong bias towards doing that, because if you have learned locality fully in your small systems, there is nothing to go wrong in the big system, except it breaks down now. But within your approximation class, you're quite safe. So this is actually a very, very important part. And there are some systems where this is not enough. I will talk about that later. Then the symmetries that was talked about yesterday. Most people, not everyone believes that, but some people most believe that. So I mean, it's a fact that the energy is invariant to symmetries. That's just a consequence of the Schrödinger equation, and these symmetries are relations of the structure, the permutation of the atoms, and also all the translation of the full structure. But some people believe in building that in the function that you build. Some people don't believe that. I believe that it's actually a good proxy, and it has been shown to have a lot of useful consequences to build in the symmetries. And one other thing that at least most people do in some way, but not as cleanly as that, is some sort of body expansion. So you take your site energies and then you expand it into terms of increasing complexity. And this is just a one body term, which is basically just stand. And then because of translation invariance, so then you have a three body terms, and there you can have a systematic approximation of your function. And you know that principle, this is complete if the order of that is the number of atoms of your system. So if you don't truncate it, this is not an approximation. Obviously, you don't want to just keep that forever. So you will truncate it at some point, but it's one useful approximation. And when you have this body order expansion, you can really see it as a function of different kind of clusters. So you're learning things of two clusters in your system. So this is going from the structure to the cutoff. So the locality is going here. And then you are learning increasing clusters. And most of the state-of-the-art models right now go to body order that are from 5 to 13 or 14. So models are very, very high body order. And actually, you need this very high body order for the most challenging cases, especially, for example, high accuracy on organic molecules. And once you have done this approximation, the simple thing you can do to construct your model, so now you want to have something that you can mash on with some coefficients, is some sort of tensor product approximation. And this is really the most naive thing you can do. So for each of these terms, you can find a complete basis with the coefficients of this basis. And how do you construct this complete basis? First, you start with what we call the one particle basis, which is just a function of two atoms. And you see here you have a function of the distances, so the radial part, and a function of the angular part, which is expanded in the spherical harmonics, which is just the basis of the distribution. And then this is just two-body, so now you want to approximate things that are higher than two-body. You just have to take tensor product of that. So if you take products of these things, all of the indices, then you can show that this is a complete basis of all of the many-body terms. So you're like, okay, what? And then you can just learn linear coefficient, and you're done. You have your model. The problem of that is, first, this basis is not invariant to permutation or rotations. So there is one thing that we haven't done there. And the other hope is that this thing scales exponentially with the order you want to go to. So you won't go to order 13 with that. Basically here, the number of products you need to do, because it's a full tensor product, scales with the number of terms. So basically, is there a more clever way of doing that? And a lot of the methods today are basically very, very advanced way for some of them to specify this basis, because all of them at the core have this tensor product operation, but they don't do the exponentially scaling tensor product. They just compute some of the terms. Important. So MACE is one sort of this specification of the full basis, and it's a many-body equivalent message passing neural network, and I will explain all of these terms. So message passing neural networks are just graph neural networks, so neural networks that operate on graphs, and graphs are just this local environment of your atoms. You have an atom, which is your center atoms, and then let's say these are the neighbors. And each atom has a label on it, and this label is this sigma here that I called, and it's constituted of three things: the position of these atoms, so this is just a vector, x, y, z. Also some fixed attributes, usually we just pick that to be the chemical element, but you can also add to be some kind of spin or charge or whatever you want. And some learnable feature that at initialization, we just take that as a function of the species, but that will be updated. And I call that a semi-local state because as the more you do message passing rounds, the more the receptive field increases. And so at the first stage, this is quite local, but then this goes a bit further. So usually most models, message passing models, go from 10 or 8 angstrom to 40 angstrom in their full receptive field today. So yeah, 40 angstrom is a bit semi-local. MACE usually is around 12 angstrom, which is actually some local models also do use 12 angstrom, so it's not that large. All message passing neural network potentials have 3 phases, all in common. The first phase is the message construction. So the way you do that is that you create a two-body embedding the states of 2 atoms. So you go on a bound, I, J, that they have states, so positions and species, and you embed it into a function with a common function. This is the M, and I will say what is M in MACE in particular. Then you sum, so this big plus can be a sum, and usually is always a sum. So you sum them of all of the neighbors of I. So basically, this for the central atom I, it's gathering all the information of its neighbors. So it's looking at every of its neighbors, and this is an oxygen. It's there. There is an in there, and then it's gathering everything there, and it's collecting this information Mi, and encapsulating this into this vector Mi. Then it's using this, so it has learned to know a bit of its environment. So it has learned this Mi, and it will update its state, sigma, to be a new state, because now it has changed. It knows that carbon surrounded with hydrogen and oxygen, so it will change state. So there is a new state, sigma I, that is a function of obviously what the atom is, and also the new information that it gathered. And then you do that n time, so you get updates recursively again and again, so you get a state that is richer and richer. Then at the end, you get all of the sigma I, and you make a readout function that just map these states to an energy, so just a scalar, and you sum. Here I sum all the layers, but you could also take the last one, and you get an energy. So this readout just maps these states to an energy. MACE is a equivalent MPNN because its internal features. So here the M and the features H, on the state. These features, they have an extra index, which are the LMs, which tells you how this feature transform under rotation, the rotation group. And it says that if you apply a rotation to your input, so you take your molecule and you rotate it, your HI will not change in a random way. They will stay in a prescribed way, which is just in a linear combination of these LM indices using these D matrices, which are the Wigner D matrices. So basically, hitting your input doesn't change your features internally in a random way. It changes them in a prescribed way. And for example, if you have L equal 1, basic features will be vectors like that. And if you rotate it, you see your features internally will rotate with it. So basically, applying rotations is not creating noise into your internals. It's actually behaving sensibly. And the energy is just the L equals 0, which is basically the sphere, meaning that it's rotationally invariant. It doesn't change when you rotate input. Okay. So what were the limitations, because that's quite old, of MPNNs before MACE? So the first thing is that this operation to create the message is only a two-body operation. And here, I mean, the most well-known equivalent matchup patching network that does that is NeQuip, which is very accurate. Basically, the fact that it only passes two-body messages means that you have a direct relationship between the number of layers you have and the expressivity. Because to build correlation, I mean, the first thing I said is that we want to approximate this tensor product basis at a very high correlation. So we want to model things that are very high body order. But if you only pass two body every time, you need to pass messages again and again to increase this correlation, this body order. So basically, you have a different direct relationship between the number of layers, which dictates also the locality of. So the more layers you have, the less local you are, and your expressivity. And this means that you actually have to pass a lot of messages. And some try to make this M many-body, but usually, I mean, all of the previous attempts were basically based on invariant quantities like angles, triplets, and quadruples of angles, which also exponentially with the number of neighbors. So you still don't want to go back to the tensor product basis and scale exponentially. And basically, MACE is a way to construct many-body in a way that is not scaling exponentially with the number of neighbors. It's actually just scaling linearly. And you can create very high body order in an efficient. And most of the MACE models we use pass 4-body messages. So if every message is 4-body, and we just use 2 layers. So basically, when you use and each layer has a 4-body message, your full representation is of body order 13. So it's a very high body order, but it's specified in a very special way. So how does MACE does that? So the way it does that is you take your message and then you expand it also in a sort of Taylor expansion. So you have the term that is just a 2-body term, which is basically what the normal MPNNs will stop at, like NeQuip. and then you go to the free body term, and then you have the four body term, etc. And then you want to approximate all of this u. And to approximate all of this u in a way that doesn't scale exponentially, you can use a linear combination of split basis that is inspired by the ACE, the atomic cluster expansion. I'm saying inspired because it has some modifications, especially in the way it couples the elements and the radial thing. So actually, it's what we call a trace, a tensor reduced ACE, but philosophically, it's very similar. So ACE, not to regress the energy, but to learn the terms in your message expansion. And the way you do that is quite easy. First, the first thing you do is you create a two-body function that is also a product of the radial component and the spherical harmonics, and an extra thing, which is the features that you pass in your message passing, because you want to do a message passing. So in ACE, you will stop here. You won't have this H, and then you get just the radial and the angular, but here you add the H. And you see this looks very to the tensor product basis that I discussed earlier. But the very crucial step is that you do a sum, which is the normal sum that all MPNNs do. But actually, this sum is very important, because now you end up with a two-body function that is only on every atom. So you see, it only has one index. So here you sum the two-body things. Previously, after creating the two-body pairwise function, we directly take the tensor product of these. And this makes the exponential scaling. But here you first sum, and this is what we call the density. And then in the second operation, we take the tensor product of things that are on atoms. And this means that you go very high in the product that you take without scaling with the number of neighbors you have. And this density trick is quite old. The first thing that proposed that was 2013. And ACE used that too, and MACE also uses that. This is a very efficient way to compute a high body order. And basically, there is no free. What do you lose? You have gone from something that is exponentially scaling to something that is scaling linearly. So what do you lose? And actually, the only thing that you lose is that you create self-interaction terms. So basically, terms interact with themselves. And actually, it's not so much a problem to interact with itself. When you fit a quite expressive function, you actually lose no accuracy. And there are work by where you can remove these self-interaction terms, and actually the accuracy doesn't increase. So actually, you have introduced extra flexibility that is actually not really hurting your model. So you take this one-body function, this two-body function ACE, and then I will skip this step. This is the tensor decomposition. And you take product of these. Quite important that you only take the products on the LMs. And then the second step, so this is solving the exponentially scaling with the number of neighbors of the tensor product basis. And the second problem of the tensor product is that it was not invariant to rotations. And the second step is to symmetrize this basis here that is not properly equivariant using these coefficients, generalized Clebsch-Gordons, which are just projections that project the many-body space to the equivariant subspace. And then you end up with this B basis, which are a complete basis of many-body messages. And depending on the nu you get messages of a body order nu plus one, because you have predicted things that are. And basically, using these things, you can just make a linear combination of them, and you get the messages. And this is how MACE does it. So basically, you just create this B basis, approximate your messages with this many-body basis, and you get something that is, you can approximate the messages to any given accuracy. So then, usual thing, you map these messages to new features using the update, just like any MPNN. And then at the end, you take these features and you make a readout to read. So MACE has readouts for every layer. So because it has two layers, E0s are just constants. Then it has the E1 and E2. And the first layers are just linear. So this is to preserve strict bloody order. And then the last layer is a nonlinear function of the features. And you only take the invariant part. So important thing is that that I want really to mention is this idea of sparsifying the full basis. And basically, message passing is very chemically sensible way to sparsify representations. So if you take a purely one-layer model, I don't really like the word local. We make things local depending on the cutoff. So I would say like a one-layer model, and you take a large cutoff, and this is your central atom, and the kind of basis you create of interaction. So you have this central atom that interacts with this hydrogen and this nitrogen, and so this is quite a chemically sensible basis. You will think that this is probably a good a quite non-negligible contribution to the energy. So you should approximate that. But you also approximate this interaction, which is this hydrogen very far away and this nitrogen very far away. So if you do the expansion, it's highly likely that this interaction, so this contribution to the energy, is quite weak. So now you have introduced a new element in your basis that basically it costs as much as the previous term, but it's probably not very important in your energy. So when you do a message passing, usually you can use a smaller cut, let's say here, so but iterate it twice, and basically the final receptive field looks like that. So it's not a big sphere; it's like a concatenation of two spheres. And now you get this cluster. So this term is still approximated, but the other term is not here anymore. And so this is why 2 times 4 angstrom is not the angstrom. So as Nicolas said, yes, they creating a very deep message passing network create very large receptive fields, so it defeats the purpose. But if you do very sharp passing like Maze, where you just do one layer, I think it's actually a quite sensible way to increase the cutoff without creating too many spurious terms. So yeah, really 2 times 4 is not 8 angstrom. And the fact that Maze creates many body messages actually decouples this correspondence between the number of layers and the expressivity that other MPLN suffered from. So if you look at, this is the 3BPA, so small molecular benchmark, and if you look at the accuracy of MPLN's models, like NeQuip or Botnet, which is a version of NeQuip, with the number of layers, you see that basically NeQuip needs quite a lot of layers here, 4 layers, to reach its peak accuracy. But in Maze, because you do the manips, you actually need 2. And so the fact that Maze reaches good accuracy just in 2 and NeQuip requires 4 really shows you that the message passing is not used to increase the receptive field. It's used to increase the body order of the representation. And obviously, these small molecules are fully seen after 2 layers, so it should just converge in 2. So this is a very sensible example of why many-body messages are a good thing. So though I have covered the theory of Maze, I will go a bit foundation models, which are one of the most exciting recent application of these models. And usually, really, to motivate the use of foundation model, I want to go on this example. So for years, when you fit your ML potential and you have a new system, you're very excited. So you start with your initial database and you fit your favorite, and then you run molecular dynamics, and this happens, everything explodes. And the only way to recover from that is basically you take the frame that explodes and you compute the DFT with it, and then you re-put it, and you hope that converges. And from experience from people in the group and other groups, these loops takes a lot of time. So in the last 10 years, if you ask someone to create a new potential for a new system, they took their full PhD to finish it, just because of things exploding. So this is very, I mean, everyone that fitted, it's even more pronounced in all potentials, but everyone that fitted potentials knows about these explosions. So can you find a way to save a bit of PhD and a bit of their lives with having a potential that is basically stable out of the box? It doesn't necessarily mean need to be accurate for your system, but you can directly simulate and maybe increase the accuracy, but at least doesn't have to suffer from this explosion. And so I will skip that. So one surprising thing that we found is that if you fit to very large datasets, like the MPH dataset, which is a large dataset that was collected over the years by experimentalists and computational chemists of basically 89 elements, so most of the periodic table and all of the crystals, so small inorganic crystals. and you fit a model on it. So this Mace MP0, and then you test it to a bunch of examples that are not in the training set. So these things is only small inorganic crystals, and you test it to various things like surfaces, amorphous systems, water, a lot of different complexity. Surprisingly, in all of these cases, the simulation is stable out of the box, so you can directly run MD without any explosion, which is actually very useful. And also, in about 70 to 80% of these cases, the model is out of the box qualitatively accurate, and in also a good portion of the cases is quantitatively accurate. There are some cases where it fails, and we have written this paper where with all of these authors where everyone is a specialist of their system, and they tried it on their system and reported things that work or things that didn't work. So you can go in the paper, the appendix, to see the different performances. But it's actually quite a surprising fact. I mean, we didn't believe this at first. So when we fitted this model, so a lot of, there was previous model fitted there, but no one had tested these models on such an extensive data set, and we were thinking that surely it will fail quite fast. We asked all of our friends to test it, and then every time they came back and things worked. So we asked more and more people to test them, and we ended up with 35 examples there. And really, this notion of extrapolation from small inorganic crystals to amorphous system or surfaces or molecular system is very surprising. It means that basically there is quite a low dimensional manifold of the chemistry where you can really extrapolate between. And these MP0 models are quantitatively accurate for surfaces. But anyone that knows a bit of chemistry knows that surfaces are completely different than bulk. Like the fact that you have a vacuum outside changes structure. And the fact that these models are not insensible for things that are so outside of their training set it was a big motivation to pursue that even further. And in particular, the Materials Project dataset is not a dataset that was made to fit potentials. It actually contains a lot of inconsistent DFT. It's not that large, so only 1.5 million crystals. So you can do better. And now we have datasets that are coming that are specifically made to train models, and you can expect a very rapid increase in performance of these models as the datasets get better. So one example in the MP0 paper was doing simulation of amorphous carbon. So again, there is only small inorganic crystals, so amorphous carbon is quite out of domain. And we compare the MP0 model to models that were trained on large databases of amorphous carbon. And we looked at different kind of ring statistics and the density of coordinations. And basically, you get things that reproduce the models specifically trained for amorphous carbon while having seen no amorphous system before. So this is one example of this extreme extrapolation that was very impressive. So why are the foundation models very exciting? So the first thing, as I said, is that they can do stable molecular dynamics out of the box for a large set of systems that were unseen. So basically, if you go on GitHub and you download Mace for your favorite system, you can out of the box run simulations for your systems and see if it's correct or not, but collect samples and maybe redo DFT. So basically, it's one of the big steps of building models for your system. Like the first few years of the PhD was to get a stable model, and this is just basically no bootstrapped with these foundation models. The other thing is that, I mean, you get good qualitative agreements and sometimes even quantitative agreements. So this really depends on what you want to do, but sometimes this is enough. And enough, it's very easy to fine-tune them. So you can fine-tune them to some small quantity of data, much smaller amount of quantity than what you will need to create a model from scratch. And then you get your high quality accuracy. And obviously, MP0 training set is not very large, and I will see what we are doing now to improve these models, and we have new generations that are much better. As I said, if you go to the Mace GitHub, and we will do some examples afterwards, and you just install it, you can take whatever system you want and run some MD, and things won't go too crazy. So this is actually quite a big breakthrough. You can even do the simulation of the whole periodic table at the same time, which is surprisingly interesting. You have a lot of weird chemistry happening. So fine-tuning is, I think, the most scientifically impactful foundation models, because when you want to produce new science, you need accuracy. You cannot go with qualitative arguments. And this is why I call them foundation models. And I know this is a debate in our community. I really don't like the word universal models, because we don't even have the universal functional. So how can we have the universal potential? I don't see how it's possible. I prefer the foundation model because it's just the starting point of accuracy. So this is why I call them the foundation models. And you get a foundation model that you train on a large set of systems, and then you fine-tune it. You continue training on a small, usually high level of DFT. And this is especially important because you know that because there is no universal functional, every system needs a different functional to be accurate to get your observable. It will be completely crazy to say that you train a model on the functional and then you will never fine-tune. Like, every scientific application will need fine-tuning at some point. And if you go in and directly fine-tune the models right now that we publish on your systems. And the challenge is then how to find robust protocols to do this fine-tuning. And I will go talk about it quickly. So when you want to construct a fine-tuning protocol, you have a few goals. So the first thing is to achieve good accuracy on your fine-tuning set, obviously. So this is under fitting. You want also to ensure robustness. So obviously all of the good things that you had in the foundation models, you want to keep it. So the fact that it doesn't explode, everything. So you don't want big forgetting, which is the usual term in the ML community. And then you obviously want to limit the cost. So you don't want the fine-tuning cost to be the same as training the full model, else it's not useful. And one protocol that we did in Maze to ensure that is the multi-head replay protocol, where you get your full so this is very large, few millions of DFT. You subsample it, and the subsampling algorithm depends both on your fine-tuning set, composition, and also other strategies that you can get the most representative set. And then when you fine-tune your model, you both train on your fine-tuning set and also you replay some of the well-chosen data. And so this ensures the model fine-tunes, it still keeps some accuracy. And it's important that you have two heads, because the pre-training set might be inconsistent with your fine-tuning set in terms of DFT settings. So you split, and doing this, basically you have a controllable parameter, which is the size of this replay set, where you can converge towards no forgetting at all, but you can also interpolate between. This is quite a simple approach, but it has proven to be very powerful, and I have examples in the MP0 paper on instances of that. The one thing to mention is that if you do the naive approach, where you just take your model and you fine-tune it without anything, it's terrible. Well, sometimes it's good, and sometimes it's not always terrible. Sometimes it just works, but sometimes you basically just lose all of the robustness of the model. So so this has proven to be very useful. And in the plot I have done, so I've taken some of the example of the MP0 paper. So here you have the pictures of all the different examples. So it's quite a representative set. And then I have models. So here you have two models, so MP0 and MPA, which is the big brother of MP0, a bit better. And here, this is the same model, but trained from scratch in blue. And these two are the fine-tuned versions. So if you look, for example, at the first example, you see here, this is the from scratch training. So if you just out of the box, and you see, and this point is the MP0 out of the box. So you see MP0 out of the box is a bit worse than training from scratch. Obviously, it has never seen this system. And since, like, it's not crazy, it's still a reasonable accuracy. And if you go to MPA, which is a bit better, it's actually as good to take MPA out of the box or train from scratch. But obviously, out of the box, you have done no DFT, so basically it's free cost. And then when you fine-tune, you see this big jump from training from scratch to fine-tuning. And if you take a bit time to look at the other examples, you see that this jump is not always as large. Sometimes it's smaller, sometimes it's bigger, but it's always at least better. And in some cases, it's actually better than training from scratch. It depends on the complexity of the system. So that's why I would recommend always to fine-tune. an example where from Venkat Group in UCL, and they train a maze from scratch and the maze fine-tune on what a higher level of theory, and they look at the number of training examples in the fine-tuning that you from scratch to get the correct density of water at this level of theory. And you see when you fine-tune, you can correct density with like 50 examples, but training from scratch you're still way off, and you need about 400 of these to get good accuracy. So it's a big reduction in the number of training examples you need. So big reduction on the cost of creating the DFT. Okay, so to finish, I want to talk about scaling up Maze to large datasets. So what we have done to train on larger datasets. So we have models now that are trained on datasets that are 200 times bigger than the Materials project. And one of the big datasets was OMAT, which is 100 million inorganic crystals. And recently, I'm part also of this effort with Meta, a new dataset that is OMOL, that is 100 million molecular systems at hybrid level of DFT, which cost 1 year of all of Facebook's server to compute. So that only a big company can do, but they released it open source, which is huge for the field. And we have models that are trained on these things. So we have a multi-head model that basically is trained on everything at once, and then it has a prediction head that is trained on R2Scan MatPES. And basically we pre-train the model on OMAT, and then we fine-tune on a huge series of datasets, so 15 of them that cover a lot of chemistry, so surfaces, reactions, materials, everything at once. In the model, we just keep this head. So we don't want to have a model that has different prediction heads, because we want people to be able to do interfaces, and you don't want to do surfaces with one head and molecules with other single model. So at test time, we forget about all of this thing and we just keep this model. And we have created a new benchmark that has a much larger comprehensive set of chemistry, the crystals with phonons, molecular crystals, surfaces, inorganic molecules, organic molecules. And these models here, MH is basically state of the art. And you see this is a competitor from Meta, which called UMA, that is quite the second best, and that was trained also on OMOL and OMAT and all the dataset at once. So you see by combining it much better. And the impressive thing is that using this head that is basically, it's better than MP0 at phonons, and we have another model, MESOF, on trained on molecules, and it's actually better than MESOF. You can basically unify molecular system and bulk system doing this multi-head approach and get a model that is state of the art. And you can see clearly the rapid increase in a few years in the accuracy in different methods with the datasets getting better and better. And my projection is that in a few years, we will have an out-of-the-box GGA quality. So you could have, I mean, you will hopefully never have to run PBE again, but you will have to run hybrid or R2Scan model. That's my guess. And final thing is about speed. So the first promise that I made is that this thing will be fast, and if you're accurate, but you're the point. So we have a large effort to speed up these things, and I want to talk about two separate efforts. So first one is Symmetrics by Jack Witt, that parallel evaluation of Maze on different CPUs or GPUs, and you can basically scale to on as large system as you want. So it's basically reaching the promise that I said earlier. And a parallel effort is a collaboration that we have with NVIDIA that are writing special CUDA kernels for Maze to accelerate Maze, and we see speed up of a factor of 8, and they are continuing their effort to write more and more optimized code for Maze, and it's going to get faster. And we have a new evaluation, also MLIP, to evaluate the Maze model with these CUDA kernels, and you get basically similar speed to Symmetrics, that is a few nanoseconds a day for atoms. And other approaches. So here, this is DIST MLIP, and you have a comparison with other state-of-the-art models. So eSend is the backbone of UMA, which is one of the state-of-the-art model, and you see that Maze is about 10 to 20 times faster than eSend currently, with accuracy that are in this paper, they scaled Maze to millions of atoms. And that's another interesting paper where they also scaled Maze to the multi-GPU, and they compared Allegro and Payne. And I included this plot because you can see the effect of basically the message passing. And so Allegro, he has a small cutoff, so I think it's 5 in the paper. So you see that when you increase the system, this is the scaling by increasing the number of GPU, and you see you have a perfect scale, no communication. And in Maze, you don't have a perfect scaling because you have twice the cutoff. So you have a bit of overhead, but you can still basically get similar. So if you look at here the speed for a system that is 4 times larger, basically it's comparable. So doing 1 message passing is not killing you, and 5 message passing, and you see the scaling is much worse. So basically, doing 1 message passing, I think, is safe. And extra thing to say is that this scaling here is mostly just a function of the cutoff. Oh. So basically, if you take a model that is twice the system size, the cutoff, basically the same recessive field in Allegro than Maze, what will happen is that you will run out of memory or be much slower. But they could have communications, but basically the amount of memory increases a lot. So message passing with 2 layers is actually less memory intensive than a 1-layer model with twice the cutoff. So you need to take into account that these 2 models don't have the same receptive field. Like this model has twice the receptive field. Okay, I don't want to talk about that. So the challenges to finish, obviously, that we train are as good as the DFT. You cannot get better than what you train on. And so we have no universal functional yet in DFT, so there cannot be a universal potential. So we need to learn how to fine-tune to higher level of theories. Better coverage of the chemical space with increasingly more accurate will give us a very big increase in terms of accuracy of these foundation models. And it's very important to get automated suite of validation for these models. So they are very famous benchmark now, but they are very narrow in what they test. And it's very important, if we don't want to go in the incorrect direction, very big, wide representation of all the things that people care about, such that we don't get misled in direction that just optimize for some metrics. And we have seen some models that just optimize, and then a new metrics pop out in the leaderboard, and they completely change their approach because it's no bad on the other metrics. So validation tests for potentials is very important. What I said about locality actually breaks down in some cases, so not everything is local. There are things where you need long-range interactions and build a long-range interaction in a coarse-grain way. You don't have to go back to the full number of electrons. You can coarse-grain that again, and so you keep the local model and you just add some coarse-grain representation, and that's coming. We have models that do that, and there are some cases where this is super important, for example, for charge systems. So locality is not the end, but it's a good baseline. And yeah, want to thank everyone for your attention, and thank you for listening.
Thank you very much for this very nice overview. I think we have time for a few very short questions. We can maybe answer here.
Reference analysis and like the E0S, and sometimes we use the isolated isolation. Sometimes we use average. How do you think of the effect of them when we use different?
So basically, what they do is they give you a well-defined limit when you separate atoms. So if you want to have the correct atomization energy, which is basically if you take a molecule and you explode it into atoms, if you want to have the correct limit that it has, then you need to set the limit of your potential to be the isolated atom energy of your DFT. Else you won't get the correct atomization energy. If you set average, what will have your model will only learn the interaction energy, so the delta atop of the average interaction energy of your model. So of your data, you take all of your data set and you look at every pair of atom, like hydrogen, oxygens, all of that has a baseline energy, and because you always explore things that are close to equilibrium, just learn a small data. So in practice, it's better in terms of performance because you learn a smaller quantity, but you don't get the correct limit. So whether you want the correct limit or not, this is a modeling. I would say that when you want to do reactions, it's a good baseline to have the correct limit when you atomize things. But if you only are interested in bulk simulations where you won't have any reaction or bond breaking event, then you average. So really, it's a modeling choice, and it has consequences in the accuracy of the model. Usually, we see that the average is a bit better in domain, but it gets the correct limit. So validation models have the correct limit because we think that because they should be somewhat foundational. It's a small price to pay. So yeah.
Continue this. I want about the spin. Just like for most isolated molecules, you usually have spin, have a single molecule like this. So, but you want to predict the molecules. Later, actually, for neutral molecules, sometimes is a low spin. So, do you think in the reference allergy in the isolated molecules, but in molecules prediction, actually no need to put a spin on. How do you think of this?
Yeah, so usually the thing to do is the atom spin in the lowest spin states when it's isolated, and this is usually good. Obviously, including this model is important when you want to study a system where spin is important, and in the new normal datasets, we have computed, Facebook has computed molecules at different spin states. And so we have models that are coming out where spin is an input. And so you can actually state to the model that you want. And that will be important when you actually want to study different spin states. But if you just want some E-zeros, then just take the lowest spin states in the atom.
Oh, okay. Last question about we usually use MACE potential to do molecular dynamics. Can we use it also do the optimization? Just like with minimal.
Yeah. You can use it as a calculator, so you can do any AAC workflow that you want. Yeah.
Okay. Thank you.
Just a curiosity. I mean, connected to the previous question. So, I mean, you said that depending on what is the property what is the system type of simulation that you want, you can take the isolated atom or the average energy as a reference or something like that. But doesn't this purpose of a foundational model that depending on your system, you have a different reference?
No, this is something you decide before fitting the model. This is just in the model. But in all of these foundation models, we take the limit to be the actual isolated atom. So all of these models are unified. You don't take that at runtime. It's just when you do a system. So if you want, for example, to only study bulk water, and you just want a system for system that, you can take the
Yeah, thank you for a very nice talk. You probably know I'm interested in like multi-fidelity models these days. Do you think there's a way to apply essentially a foundation model to the chemistry exploring around you, and then have a specialized models at the surface where the chemistry is happening? Do you think they can be mixed in some ways?
I know that some people are interested in that, so I haven't tried. Somehow it's a bit connected to the usual interfaces, and then you just basically end up having an interface again on the two things. So how do you treat the interface? I think it's probably interesting, like to use these kind of multi-head things and then specialize the atoms with different heads. But you need to be very careful in terms of interfaces. And then, I mean, I don't know much of the QMM. It's a mess. So if you want to go there, yeah, I think that's the danger. And this is why I in these models, I say that it's a single head model, and I actually publish the other heads. I'm not sure, but this is something. If you're interested in, I would be very interested in seeing how you could do this kind of multi-head approach. Yeah.
Great. Thanks. Just want to remind you that we also have a panel discussion, so this kind of questions could be also good for the panel. So I think now is the time for tutorial. Also, if you are, yeah, sorry, there is a break after this. Yeah, I hope you can manage.
Can people see on the screen, or I will? I don't know how to zoom. Wait. Oh yeah. Wait. Maybe that's too zoomed down. Is it better? Thank you. So I have 2 tutorials. So how much time do I want to time? Okay. 40. Okay, 40 is fine. Okay. I will just. So the 2 tutorials are quite extensive, and if you are interested in like learning the basic of Maze, I encourage you to go spend a bit of time on every step. So I will just go to the essentials part because it's quite long and we don't have a lot of time. So I will focus on the essential. The first notebook just goes over all of the first steps to build your first potential with Maze, and you start by understanding how to your dataset. What are the Maze parameters to tune when you fit your first model, and how to test your accuracy, and then molecular dynamics with Maze. So this tutorial basically the purpose is to fit a Maze model for these electrolytes, molecular liquids. So you want to end up with a model that can do this simulation of molecular liquids, and these are the small molecules that are inside, and we want to study, for example, like these can be useful in batteries for electrolytes, and you want to have a potential to be able to study them. So the first thing is that you want to code configurations to be able to have a training set. So the way we did that is by, for example, running MD. So you start with the smiles, then you generate the 3D structure from the smiles, and then you run a bit of MD. You could now use the foundation models, but in the past you use either DFT or you can use a classic to get samples, and you end up having this database that is a database of 5,000 structures, and in these structures molecules, and then you have small clusters. So we've made this database like that. And if you look at the database, which is an XYZ file, what it has inside is, so this is the Z in my talk, the positions, which is the R, so the XYZ of every atom. So this is XYZ for every atom. So, okay, that's nice. But you don't have energies and forces, so what do you fit to? So now you need to go to your favorite DFT code to generate the energies and forces. T is very expensive, so we won't do that live. So what we did is instead of we are going to run XTB, which is a semi-empirical quantum a tie binding code. So that's the distribution of the datasets. So it's very important. I made this introduction to remind everyone that when you fit a model, you need to understand your data. Data is key, and you need to be an expert on. And if you just take the dataset online and just try to fit your model, it won't work because you don't know what to expect, you don't know what to tune. So really understanding your data and doing all of this. This is also of Maze, obviously, but it's the very most important first step in fitting any ML potentials. And here I look just at the distribution of the size of the cluster of different size, and the one are just isolated molecules, and then you have dimers and trimers, etc. And so this is covering the interaction between different molecules. When you are studying these molecular liquids, there are two main effects to the physics. There are the intra and the inter interactions, and so between molecules is very important. And so this is why you include this cluster to be able to scan how different molecules interact with themselves. This will find the chemistry. So this is the different composition that you have. So you have covered quite a large range of compositions in this dataset. Okay, the first thing is, how do you label your data? So usually you will go to your DFT code, take these structures and evaluate them, single point. The first thing, as the question mentioned, command to always compute also the isolated atoms for your system. So you take all of the species in your dataset, you put it in a box in vacuum, and or if it's not a periodic code, just the isolated atom in vacuum, and you get the energy at the lowest spin of this isolated atom, and it gets these E0s here, which are the reference limit of your thing. And this will be used in Maze. You are off, turn it on or off, but I always suggest you compute it because it's very cheap and you never know if you want it or not at train time. What Maze will learn is just the atomization energy. So you take your molecule and Maze will dot regress the total energy. So the total energy, if you look at its codes, it can be huge depending on how you do the pseudopotentials and everything. So you don't want to regress a target like that. And removing the isolated atom is actually a big normalization trick first to learn, but it's also a big modeling trick because there is a lot of physics that is in the isolated atom that you don't want to learn, because this is, again, in this idea of coarse graining, and coarse graining the DFT is also putting a reference. It's actually a very big step in the coarse graining. And so you just regress this atomization energy. So if you take you sum all of the isolated energies of the hydrogens in your system, of the carbon and the oxygen, if you have just these elements. And then what you regress with Maze is this. You can also pick the average energy, and instead of putting this EAH to be the sum of the isolated atom energy from your DFT code, sum of the average energy of hydrogen in your dataset. So basically, you look at all of the hydrogens in your dataset and you look at what energy in average they have. So you just do a linear regression, and then you take that and you see that if your potential, depending on the composition of your dataset, you get different values. Because if everything is close to, I don't know if I can write, but if everything is close to, you will get an average energy that is close to the minimum. And if you explore a wider range of interaction, then you get interaction energies that limit the isolated atom. Okay, so we have evaluated the E0s with DFT. So here I'm creating C and O with ASC, and I'm calling it isolated atom. So this is an important step. So there are two ways to put the isolated atom. You concatenate it in your dataset. So you just add it to your XYZ file. So this is exactly what we are doing here. We are just adding it to the database, but you need to add a new info config type to specify to the code that this is the isolated atom. And you see, before we just had 5,000 structure, and No, so we just added the free isolated things. Okay, now we have the full database. So let's call XTB. Again, XTB is just for the purpose of this notebook because it's fast. You will not call XTB. In reality, we'll call your DFT. And you compute the energies and the forces for every structure. So you loop over your database and you compute. Here, this is just 15, so that is fast. But you see, now you still have, if you look at every atom, you still have the species and the positions, but now you also have the forces here. And there should be the energy, yeah, here. And also the energy. So now you have, I've written them with keys that I need to remember because this is very important to give to Mace. You need to be able to tell Mace what is the name of the energy and the forces that you have written in your file. Okay, so now every structure has an energy and the forces, and you also have your E0s. So you see this is the isolated limit of whatever XTB does to get. So if you look at the total energy, look, it's a huge number. So this is in EV. So 1,000, you don't want to regress 1,000 with a model because it won't learn well. Now, if you remove the isolated energy, you get something that is a factor of 10 smaller. And if you look at it in a per atom quantity, because the model fits per atom, then you have something that is order 1, which is basically what you want to fit. And it's very important that when you try to fit your new model, you compute these atomization energy in your dataset per atom, and you see that it's order 1. Because if it's not order 1, it's like 100, then there's something wrong with the E0s. And if the E0s are wrong, the model will not fit as well. So do compute the atomization energy and get something that is order 3 to 4 to 5. It depends on the system. Just for context, in the case where you use the average energies, then this number will be around 1 to 0.2. So you see, you get another factor. And the fact that this is a smaller number means that it's actually easier to fit, obviously. It's a smaller range, but it means also that the limit won't be correct. So you have lost something, and you need to be aware of that. It's not necessarily bad, but you need to be aware. Okay, so the next thing, you have prepared your data. Now you want to fit the Mace model. So what are the hypers to choose when you fit your first Mace model? And I have written a quite detailed text on that. So I won't go over everything here. So please take the time if you're interested in reading this text. But basically, what you need to do is it's called this the Mace run train script, which is the script that they train Mace. And in that, you have different hypers. And these are the most important ones in Mace. So the first one is the number of channels. And the number of channels dictates basically how wide the network is. And usually we interpolate between two values. So 64 is the faster model, so small. And 256 is the largest. And usually the default is 128. And I will recommend everyone to use 128 for their first fit. The other parameter is the max L, which dictates the equivariant of the message. So you know in the Mace equation, we created this M by summing the B bases. And if these M's are only invariant scalars, then max L equals 0. And if then you want to include vectors too, then you go to max L equal 1. And if you want to include higher order spherical vectors, then you can go to max L equal 2. The higher you put the max L, the more expensive the model gets, but also the more accurate it is. Max L equals 0 is really the fastest. So if you want to go for the fastest model, you just go 64 and L equals 0. It won't be the most accurate. And the baseline model that we use, and the foundation models are also that size, is 128 for the channels and max L equal 1 for the symmetry of the messages. And when you start a new project, it's safer to start with the default, fit your dataset, and then if you need more speed, then try to fit again with a smaller model. It can be, if for example, the model is too small to fit your dataset, you can spend a lot of time trying to improve something where you can just use a bigger model. So it's better to start with big and go to small than starting from small and go to big models. The cutoff is the receptive field in a single layer. So if you use 2 layers and the default is 2 layers, this will be the full receptive field is twice the cutoff. And the values are between that I will use are between 4 and 7. 7 is very large. The average is 5 or 6. That's the usual thing. It depends on the chemistry. If you know that your chemistry is very short range, you can use 4. And if you have a bit more long range things, you can use 6. The foundation models are 6. The number of interactions or the number of layers. And so in MACE, this is default to 2, and I recommend not to change. The correlation is the correlation plus 1 is the body order of the message at each layer. So the default is correlation order 3, which means that MACE will pass 4 body messages at each layer. So I will skip that, and I will go directly to the training input. So you have your database. So here I've just taken the first 200 configurations to be the training set, and then the rest to be the test set. So I split into training and test. And this is the input to MACE. So this is a YAML file. The first thing you want to fit a MACE model. So model equal MACE. This is for the purpose of the notebook because it ran on a small GPU. This is a very small model, so 32 channels and max L equal 1. The cutoff is 4. Then you need to name your experiment. So here, this is the name of your experiment. These are the dictionary where you want the code to write files. So the code will write the model, the checkpoints, and also the different logs at these checkpoints. The train file is the path to your XYZ file, so to your database. So you have the train file, the test file, and if you want a validation, which is something that you test every set of your training, but it's not the test because the test you shouldn't look at it before, or else you contaminate your training. You can also pick this will pick 10% of your training as a validation randomly. Then these two are some of the most important key part because a lot of the problems for newcomers is there. You need to put the right keys where you've written the energies and forces in UXIZ to MACE. Else it won't know where to find them. So make sure to put the keys there. The batch size is because we are training MACE with a stochastic gradient descent, so it's estimating the gradients by small batches, and this is the number of structures you want for every step of the stochastic gradient descent. And usually, the larger, the less noisy the optimization is, but you don't want to go too large because you run out of memory. So the values I will use are between 64 and 5. So try to go as high as your GPU allows it until you run out of memory. The maximum number of epoch is the number of, every epoch, the stochastic gradient descent goes over all of your training set by batches, and then it evaluates the validation set, and then go back and train on all the training set. And so number of epoch is the number of time it does that. So here it will do that 100 times. It's actually not the best thing to look at because depending on the size of your training set, you have widely different number of training updates. So actually, when you do train, so let's go to the training. So this interface is just to train through Python in the notebook, but in reality, you will just use your batch file and you do the MACE run train command. So here I'm just calling it through Python. And I'm training with this configuration that I've written as a YAML file. And here, here I have started my training. So this is the log file, and it will tell you, okay, that's the MACE version. Please always use the latest version before creating an issue because then I cannot. Most of the time you have a bug, I fixed it in a new version, so make sure to do that. Here it tells you what keys it has used to find the different values. So this is very important for debugging. You can check that it looked at the right keys. Here it says that it found 200 energies and 200 forces per structures. So you can check if you have like one missing value somewhere and this is weird, do double check here. And it also says that there is no validation currently, so it will randomly take 10% here. So it will take 20 structures for the validation, and now the training set will just be 180. It will also tell you that it's using these E0s from the data, so do check it's using the right E0s. Here it's the model sizes that you have picked. So it's a 32 channel, max L equal 1, it's 2 layers, the body order is 4, and the number of parameters is that. And then the thing I wanted to show you is the number of gradient update. So the number of gradient update is the number of time the model parameters will be updated. And it's a function of the size of your training set, the batch size, and the number of epoch. But it's actually a better number than the number of epoch, because if you have a large set, like, I don't know, OMOL, which is 100 of million, obviously you won't do 100 of epoch. It doesn't make sense. So what usually I aim for reasonable data sets is to have a number of gradient update that is between 100,000 and 1 million. So this is usually, so you look at this number and you see if it's between 100,000 or 1 million. And usually that's a reasonable number of gradient updates to start from. And if you see that this is not enough, I will tell you how, then you can increase that. So then you start your training, and you see the initial loss, which is very important. This is the loss of Mace when it's untrained. And because of the way Mace is done, basically, this is basically the accuracy of the E0s. So you see that you make an error on the energies of 6 EV at start, which is basically the size of the atomization energy. And then it trains, and you see the loss goes down. So here, this is a very small model, so it takes less than a second to do 1 epoch, because it's a very small model. But I'm not doing the training now for the sake of time. But you see that it's improving. So it started at 2000 millieV per angstrom on the forces. This is on validation set. And then it's going down. And then you go at the end. And this is the test set error. So you get a model that is 173 millieV per angstrom on the forces and 9 millieV per atom on the energies. So keep in mind that's a small model. So you get a table that is telling you the accuracy on your training set, on your validation, and also on your test. So you can look at if you had overfitting. It's normal that the training set is better than the test set. Obviously, you have fitted to it. And usually this is not so much problematic. The validation set should be the same order as your test set if you have chosen it well. And it's quite important to look also at the relative RMSE of the forces, because depending on what's the magnitude of your forces in a data set, like if you have very big forces, 100 millieV per angstrom could be completely different in one case or the other. So it's important to look at the relative error. And usually you want the relative error to get good observable, you want the relative error to be below 20%. So below 20%, you have a usable model. The most accurate models go to like 0.1. It really depends on the system. There are things where forces are easier. But if you're above 20% in relative error, then you might want to increase a bit either the size of your model or the size of your database. Okay, so now we have models, and it tells you here that it has saved models to this path. So it has saved models there. So now we can go on and evaluate the model. So there is a script in Mace. Okay, now it's bugging again. That's called, actually I can use the pointer. Yeah, that thing, which is just a function to evaluate XYZ file with your save model. And the way it does that is you give it the XYZ file, you give it the model path that it has saved, where you want to write the output. And here, if it's CUDA, it will evaluate the model on the GPU, and if it's CPU, it will evaluate the model on CPU. So here we are evaluating the training set and the test set. Okay, this was done on CPU, and then we are doing some plotting. Okay, so this is the correlation plot for the model we've just trained. So this is XTB, but it will be DFT, and this is Mace, and this is basically every forces of Mace and every forces of, yeah, okay. every force set of FTB, and you see, okay, the training set is a bit smoother, but the test set is quite all right. And you see here you have the 0.17 milliev per angstrom error that we've seen on the table. You see the energies look quite reasonable. So always plots. I like these plots, and actually now they are generated automatically in Math because you can see outliers. So if you see everything is good and then you have a few points there, do look at these points because in a lot of cases it's just that your DFT didn't converge and you want to remove them. So yeah, do look at, and you couldn't see that with just the RMSE. So do look at the plots to see outliers here and there. 0.01. Yeah. So two good questions. So the learning rate, I will recommend to keep the default to 0.01. In some cases, you want to go to a bit smaller, like 0.001. But I think this is quite niche. So in most cases, the way to see if you have a too high learning rate, if it's your validation set oscillates too much. So if you have the validation metrics that you log just jumps up and down all the time, then try to reduce a bit the learning rate. And the weight decay, I think usually just take the default. You might want to reduce it, but this is very advanced. So the only case where I think this is something to tune is when we do fine tuning, and I will go there afterwards. But when you do from scratch fitting, don't change it. It has an adaptation where if the validation set plateaus for too long, it decreases. Yeah, and you can also use another optimizer that is that we've implemented called scheduler-free optimizer that does the scheduling also. So for doing that, you just go to. So it's 0.01 only at the beginning, and then yeah, but usually it never goes down because 0.01 is quite. Yeah. So it really. So if you do that, the optimizer will change, and it won't be the normal Adam optimizer that we are using. It will be the scheduler free, and this will have a smooth scheduler. And actually, I have good experience. It's not the default yet, but I might make it the default. Yeah. But generally, I would say that for all cases, just take the default. It's very rare where you need to change the default. Like from all of my experience, I know a very rare amount of person that had to change the default. Okay, so here, if you look at that, you're like, oh, I mean, this is a quite good model. I mean, it's very hard. Don't take ML force fields are all about computing observables, and RMSEs are just proxy to that. It's actually a very nonlinear path toward going to the observables. So I would say that it's a very, very early indication. But to validate your model, there is nothing else than computing the actual thing you care about. And at least having some observable that are proxies to that. And one observable that is a better proxy to, for example, getting the density of your liquid right than the total RMSE is the intra-inter RMSE on the forces. And this is very important. So if you look at your molecular liquid, most of the forces inside are just dominated by the oscillation of the bonds. And these oscillations are very high in magnitude. And actually, the model is, and they are very easy to learn. And so the model could just fit that, but not fit the interaction between distant molecules, which is actually the most important thing when you're doing, you want to do, we want to get the correct density. So one way to do that is to look only at the error of the forces between molecules, which we call the interforces. And so basically, it's the forces between molecules, not between atoms, but between molecules. And you can look at the error compared to DFT. And these are the errors of the intra and inter. And here, this is the vibrational forces, so the one of just on the bonds. And you see they are quite good. I mean, mostly the RMSE, all the RMSE comes from that. And in terms of relative, it's like 7%. But this is the inter. And you see, directly, it looks a bit worse. Like, it's much harder to learn the inter. And the reason why it's much harder is because they are much smaller in magnitude. So you see here, this goes from 30 to minus 30, and here this goes to 2 to minus 2. So you see it's 10 times smaller in magnitude, the inter, because most of the interactions are dominated by the bonds. And this is getting that right is what entirely gets the density right. Like if you can get the bonds a bit off, but if you get the inter right, you are right in the density. It doesn't matter. And this is actually how some potential like MBPol does that. Like they do this molecular body ordering and they just get the inter right. So fitting that is actually very important, and that you can see sometimes it's quite off and the relative error is not that good. So here you might want to increase your system size. If what you care about is the density, it's not terrible. Like we have gap models fitted on that, which are much worse, but yeah, this is a very small model, so you might want to increase it. Then you can go and run molecular dynamics with this model. So here I've run a bit of molecular dynamics. So it took 1 minute to do 2,000 steps. And you can look at the, I hope this will work. No, because I need to run the rest. Okay, it didn't work. You in the notebook you can run the XTB also, and you'll see that it's much slower. It's not, XTB is still much faster than DFT, so obviously you won't get a very big speed up. And then you can look at is the dynamic that you've just run accurate, and you can look at the RDF. So this is the RDF of the MACE MD and the HO RDF and the XTB, and you see that the peak match. I mean, RDF is also one very easy observer to get. So this is not saying that the model is perfect, but this is the series of tests that you can run after having a model and before computing the full density that is a bit more challenging to get. One interesting thing is that these models, because of their locality, but also because of how they are built, can just directly do extrapolation from clusters to bulk. And this is very important because bulk are usually quite expensive more expensive to run, and there are some DFT codes, non-periodic codes that can only do clusters, and being able to train on clusters, get the interaction energies and interaction forces on the clusters, and then directly simulate a bulk simulation is a good extrapolation. And here, this is taking just a cell of these molecular liquids and directly running the bulk simulation. So I guess this won't run either. So I will run all of the code, and then I'll go to and show the movie afterwards. Okay, so in the meantime, I want to go about to cover the fine tuning. Just wait the time. Okay, I have not much time, so so this is the very naive introduction to the training from scratch. But I've talked so much about fine tuning, so I need to explain to you how to do fine tuning. I think training from scratch is quite narrow application right now. It's mostly to validate a fine tuning example, and I would recommend everyone to do a fine tuning. So in these notebooks, I go over 3 concepts. The first one is iterative training, which is the usual way people have done training models in the past 10 years, which is you start with an initial database that is a small database. So here we have a database of on 50 configurations. So before we had 5,000, but let's say you just started your PhD or your project and you just have 50 things, 50 configuration collected. You go on and you feed the same MACE model, you train it. Okay, it trains for a bit of epoch, and you have this error on the test set, and you see, I mean, it's only 50 configurations, so it's much worse than before. So before this number was 170, and this is 400. You have, so now how can you include more configuration from that to improve that? And this is what the iterative fitting will do. So you take your model and you run some MD. Okay, it's already stable because the model is quite stable, Mace is quite stable, but it's not super accurate. And the way to see that is you can take your MD that you've just done and evaluate some frames with XTB, and you see that there are some configuration that may predict to have a low energy, and actually they are quite high in energy with XTB. And this is because the model is not yet accurate enough. So you can sample some of these configurations here that are incorrectly predicted, recompute them with XTB. And this is this iterative fitting where you start with an initial training set, you fit your model, and then you rate MD, you look at the configuration, you recompute the reference, you refit the MD, and slowly you have different generations where, okay, here, this should be high in energy in your reference, but it's low, so you add it back, and then now it gets perfectly good because you have a new generation model, so you keep improving like that, and you end up with a second generation of model here that is a bit better. Okay, maybe that you want to improve, so you will find that configuration and include it, and you finish with like the generation 15, or usually it converges faster than that, and this is your final model. So this is the usual iterative fitting strategy. The second strategy that people use, so this is the second generation of model that you fit to. So here I added the new configuration that I've collected through the MD, and I've rerun MD, and you can evaluate the configuration that they are better. The second fitting strategy is the active learning strategy. So when you do active learning, you want a better way to find new configuration to add to your training set to improve your model. And the way to do that is to get a proxy to the uncertainty of your model. So how confident is your model in predicting the energies and forces for this configuration? And one seed for that is having a committee of model. So instead of fitting one model, you fit like 3 or 5 that have a small difference in the way they are initialized, in the selection of data. So you get a sort of random set of initialization points, and then you fit the model and you get a committee. And if you get a large enough committee, you can get the uncertainty that is coming from the limited data for a new system. Yep.
Do you see any difference whether you use builder and committee of models by changing the seed rather than by subsampling or something like that?
Yes. So usually it's changing the seed, I would say, is the least amount of variance that you get. So usually I always recommend to change the seed and change a bit the subsampling of the data. So the combination of the two is the most effective.
But once you calibrate onto some validation set, do you think they more or less are the same, even though the calibrations probably are not going to be
Yeah, we don't have much more experience with that in Mace, so I wouldn't say. I think it really depends on your training set. There are things where we see seed variation is actually enough variance already to calibrate, but some other time not so much. I would say that when you change the seed, so the way you do these committees is that you just need to change the seed here to different values. So this is the model 1, and this is the model 2. So you see I've changed the seed number, and changing the seed number will both change the initialization and the training set sampling. It will do both of them at the same time. So you just need to change the seed here. And okay, and then I train the 2 models, so with different seeds. So now I have 2 models. Okay, this is a...
So that seed is used for both?
Yes, it's used for both, exactly, yeah. Okay, then I can train my model. I can do the MD of the model and get the committee disagreements to get the variance, and the points where the disagreement is the highest, you can select them to add to your DFT, to recompute with your DFT, and then you train again a new generation of model. And basically, this is a good proxy. Like instead of just randomly selecting configuration in your MD or waiting for it to explode, you have a proxy for the uncertainty to get there. And this is the second most popular way to fit potential with active learning. Obviously, you want, if this is just a committee of 2, you might want 5. I think 2 it's not you want to get a true uncertainty, you just get disagreement, but usually it works quite well if you just want to select configuration. So, and one thing that I didn't say is when you run the MD, the log files are a bit, when you run the MD, you can out of the box create a calculator for a committee. So that's quite important. So here I just add the path to the three models of my committee, and I create a calculator. So this is how you create an ASC calculator that you evaluate with ASC. So you do from ASC calculator import calculators, and you put the list of paths, and directly it will output the variance of your committee. So that's quite easy to do a bit of active learning. Okay, you can run the committee. So this is a fun thing where we run MD with the committee and XTB and track the variance and the true error, and you can have a look at if they agree or not. I mean, it's just a small committee, so don't expect too much. But you see here that some of the spikes in the estimated error correspond to some of the true errors. Not always. It's if you want really a good estimate of the error, you need large committees. But here you don't really care. You just want a way to discriminate good configurations to add. So it's not super important to get very good. So that's the active learning strategy where you fit your model, you run MD with the committee, you select the configuration with the largest disagreement, you add it again to the training set, and you fit again. And then this converges in different generations. Okay, just last thing is the fine-tuning. So I think with fine-tuning, you can basically get these much faster, this generation. And what you have to do is you can import a version model. So this is Mace MP. And you can import the smallest model. So this is the fastest version. And you can directly run MD for this system. And it has never seen molecular liquids. It runs Table's molecular dynamics for that. So you haven't trained anything. It's just the foundation model you have imported. And then you can compute the RDF. And you see the peak is a bit tilted. But it's because MP is trained on PB and not XTB. So it's probably the Mace MP that is correct. But for the sake of that, let's say you have trained your model on PB and you want to fit it to a higher level of theory. So this is a good proxy. So let's go to Mace and fine-tune this model. So it's exactly the same input as before, but you just had a new key here that is foundation model, small. That means that you don't want to do a training from scratch. You want to do a training with the foundation model. And here you can do multi-head fine-tuning true or false. So this is if you do the naive fine-tuning where it just restart, or do the multi-head thing that I explained in the talk. So here actually the training that I've done was that false. I always recommend you to train with both true and false when you do your experiment, just to have a baseline. Okay, it has trained. Actually, I've restarted that, so should I have that? But probably it won't work. Okay. You can I've trained the model before. You can run the MD afterwards with the fine-tuned model, and you can look at the RDF, and you see that now after fine-tuning, the RDF shifted back to the right value from XTB. So basically, fine-tuning got you the correct observable with a few samples, and you can run molecular data with your fine-tuning. Yeah. This was without. Yeah. Actually, I can run everything, but actually, one sec.
you do it live. That's the chaos, but not sure some started already.
So time for coffee.
Just at any point before the next tutorial, please just run again git pull, because we made small updates just like many minutes ago. So thank you.
I know it's short time.
It's fine.
But we put coffee breaks on purpose along, so it's fine. Late,
there, and he's going to use this or this one? Okay, this one just for the replies to the answers. Yes. Okay. Oh, I think that we can start this session, and it's a pleasure for me to introduce Jonathan Schmidt from ETH Zurich. Jonathan is a research fellow at ETH, and he will talk at accelerating material science with high throughput techniques. High throughput everything. Okay, the floor is yours, and thank you.
Yeah, thank you. Thank you very much for the kind introduction. And yeah, so I mean, I will talk about high throughput searches mainly, and by then generally have high throughput calculations. And I mean, with, I guess, in comparison to maybe a decade ago, most of the things we do are already high throughput without even thinking about it. And my expertise is mostly in inorganic crystal structures, and I mean, using machine learning and a lot of density functional theory for these kind of systems. So this is also what I will focus on. I think that a lot of the concepts I talk about, I mean, are also applicable to a lot of other material systems. And yeah, to start off, high throughput. So I mean, right now, if we build a smartphone, we need around 50 elements to create all the different materials required for the tech to make it work. And so if we're looking to improve upon this, then of course we also have to scan the whole periodic table. And I mean, with 50 elements, we can already have combinations. Of course, this means space grows factorially. And so we really need high throughput if we want to explore that efficiently. And so to start off, start with some very simple high throughput example. And so when we could look for some different materials that would be very useful for applications. So for example, been a lot of people who have looked superconductors, can need some better p-type transparent semiconductors, or maybe some better permanent magnets or solar cell materials, batteries. But in the end, we know what we're looking for in terms of crystal structures. At least they usually need to be thermodynamically stable in our environment of application. And that's like the absolute minimum if you want to find some new material. Throughput search for anything that needs to be thermodynamically stable or at least metastable in the environment that we are working in. And so, I mean, how do we, if it's thermodynamically stable, we can first look at the elements and basically at the energy of our elemental systems. And then we can plot a phase diagram, and we can line between our two elements here. And then if we calculate any new molecule or crystal structure, we can calculate the formation energy. And then with this formation energy, it's basically the distance to this connecting line here. And then if the compound lies above the, this connecting line, then it will likely decompose in finite time. And then we can next concept, so we can, if we find some new system with a mixture of the two elements, and this system actually has a lower energy, we can redraw these connecting lines, and then we have what we call the convex hull. And so we could extend this concept in 3 dimensions, 4 dimensions for quaternary systems. And so it's just the same principle that now if we calculate a new compound here, it will the collinear combination of the two endpoints of the connecting line. And we can also calculate this distance, and this is the distance to the convex hull that would be gained if we have this decomposition. From the experimental compounds that are, for example, in ICSD or the International Crystallographic Database or in COD, that most of these compounds are either on the convex hull or close to the convex hull. And so in terms of basic high throughput, this is our best predictor if we would look for some new crystal structure, at least the first one that we would start with in terms of filtering. And yeah, so we're looking for these new compounds that lie below our known convex hull, and then we just have to redraw the convex hull, and we could recalculate all the distances. And now, of course, we use density functional theory. So it takes some crystal structure. We'd want to find the local energy minimum. And then once we have found that, we can evaluate the energy, and we can put phase diagram here. And of course, these, geometry optimization steps, cost some computational time. And then if we go to high throughput, this can quickly become a lot. But so just to do basic example, we can take an existing known crystal structure. Here we have a composition of ABC3. So that we could replace with other candidate elements. And then we are already at 500,000 combinations. So this combinatorial materials libraries that we can and that grow very quickly. And we can calculate all of these with density functional theory. So in this case, the cost might be around 1 million CPU hours because these structures here are very small. And we can look at the distribution of these distances to the convex hull. And we can see that we have a few hundred here that are actually thermodynamically, thermodynamical. And then we have a lot of compounds, of course, that are not really interesting from a materials perspective. And so this was basically the most basic example we can high throughput search. So conceptually, we've generated some materials library. So with the basic combinatorial approach, so we just took the prototype structure and different elements, and then we just directly used DFT to calculate our target property, in this case, the distance to the convex hull. So we didn't have any specific application in mind. The only fit was, is the structure stable in the end? And so we could have maybe also used some further physical priors. We will look at this later. For example, we could have checked, are the oxidation elements we put together sensible, so that we have a neutral structure based on common oxidation states. And so, each of these single materials here, of course, it's very easy. I think basically, if they have the vast documentation and the license, they can, probably takes them at most, even if they haven't run VAST before, takes them maybe 30 minutes. So they, do this for a single crystal structure. But of course, if you do it for hundreds of thousands of structures, then this quickly becomes a bit more complicated. And so we require and a lot of high performance computing resources in the end. Now, of course, we can try to make this a bit more complicated. And so right now, instead of having a step, we could try to make it more efficient by adding another filtering step that is cheaper to do. And so this is already quite some time ago. So, there were basically the starts of graph networks, but people were still working with the composition as well. And so we can take, for example, the energies we get from 20,000 relaxations, some very basic machine learning model on this data, and then or some decision trees, and then we can use that model to predict all our other 500,000 combinations. We can just run some DFT relaxations on whatever compounds that are left close to stability and that are still there after this first filtering step, so we'll have to set some cutoff. And it's kind of the next of the high throughput searches that usually we like to go from having some very cheap filtering steps. Nowadays, these are nearly always machine learning models, to then have expensive ab initio filtering steps, and then maybe some higher quality functionals or something more accurate. And now, of course, not so extremely efficient. We can, for example, have an update process here, so we retrain regularly after a few calculations, or we could do some active learning. I think we already heard a lot about that and might hear some more about this in the conference. Now, if we do this high throughput search, did we actually find anything useful, or are we likely to find useful? So I mean, we use DFT. So we have our Born-Oppenheimer approximation, of course. Then we calculated everything at 0 temperature, 0 pressure, and we have our exchange collation functional, typical high throughput search. I mean, then this is usually the PBE functional. It has been for a long while. And if we look at the errors for formation enthalpies here, we actually have 210 volt per atom. And so, of course, if I would come up here with a universal force field and say it would have an error of 210 electron volt per atom, this would be quite large. But this is the, accuracy with respect to experiment we're actually working with. Now, of course, this is actually based on very little experimental data because there are not so many measured formation. So also in terms of machine learning models, nobody would actually accept, this as a good validation set because it's so little data. But it's what we're working with. Of course, if we look at differences of structures that actually, have the same chemistry, then the energy differences there, might have some smaller errors. And then, we could go to some more. So Materials Project and Alexandria also have a few 100,000 R2 scan or respectively scan calculations. And with these, the errors for the formation enthalpies would be reduced a little bit, and maybe 100 millectron volt to 140 millectron volt for scan. Now, this is only the first step. So if with some experimental colleagues, they have to consider a lot more things. So we have to consider kinetic accessibility, energy barriers, what are the possible reaction pathways depending on the precursors we are using. There's also, some extra steps here where we can help with calculations. And by then, in the end, we're still left with all the experimental complexity where even if our calculation should be correct, it's actually thermodynamically stable. There's no easy way to say if, the experimentalist will actually be able to choose the right pathway to arrive at this compound, maybe some energy barriers. Most likely, if it's one of the more interesting compounds we predict might be some hydrogen hydride superconductor, some nitride superconductor, for example. Most still don't have the facilities to actually synthesize that. And so, often it's not so useful to, look now at this here, even though, usually in high throughput searches in the paper at the end, we will look at a few example materials and describe them in more detail. But the main, output in terms of material science is distribution of this data here. So that if we know we have this amount of materials here of new perovskites that are close to the convex hull, we can say, okay, based on the errors we know, depending on the availability of experimental resources, we can make create some expectation value and say to our experimental colleagues, maybe, okay, you're likely, maybe if you try 50 compounds here, maybe you will get 5 actual crystal structures. And so it's quite important that, with the accuracy in terms of, the typical DFT we use, that it's actually quite challenging to predict a single new material and actually guarantee to someone that will be synthesized. And in terms of high throughput searches, we more like to look at distributions of data. And so we can summarize this a little bit. So of course, in order to arrive at our data, we really require and resources. So we look later at, what frameworks we have available for automation. And also during the tutorial, we are going to use some automated workflows. Then also, how can we obtain these resources? And then, of course, we have this filtering. So usually we have multiple filtering steps. This can get quite complex often. Usually we even have different levels. Just in terms of DFT convergence, or let's say for what we would normally just say, okay, we relax the geometry. And then, of course, we can, have a lot of physical priors in terms of, this material, just depending on what specific material we are looking at. And then, lastly, we have this point about saying, okay, we actually want to focus evolution of the data and maybe not a single result. And then, maybe the most important point here, most of the calculations we might create will not be interesting from materials perspective in the end, but it's data. And none of the machine learning, and we saw before, of course, works without the data. And so we need, millions of calculations that somebody runs. in order to create our universal machine learning models. And so this is the next point. I mean, we're going to look at just some example, I mean, from our work, how, I mean, then the data's original purpose can take on a bit of a life of its own. And so we can see what happens if we scale up this approach of prototype-based high-throughput searches. Looking at these perovskites now, and we can just look at a lot of different prototypes. So we look at the, I mean, around 600 binary and close to 2,000 ternary we arrive at around 900 million combinations. And then we can add some quaternary prototypes here, and then we have around 30 billion combinations. And so now the approach, the approach is this one. Hello? Yeah, okay, sorry. Yeah, so, okay, actually, let's see. Yeah. Where was it? Yeah, and so the approach is going to be exactly the same. And we have our, okay, no. I will try, just tell me again if I fail. So yeah, no problem. So the approach is going to be exactly the same, just now we have some crystallography instead of a basic, I mean, fully connected network that will also predict our stability. So I mean, there is some, of course, one can use some universal force fields for this nowadays. When we started with these, force fields didn't really exist yet. And even nowadays, it's a little bit slow, so you will have to calculate in some extra resources. If you would use universal force fields as a first scanning step, still have to do your 13 billion geometry relaxations, which, I mean, even with universal force fields, costs quite a bit of computation time. And so we directly predict this. Give you the timeline. So this was the first plot I showed you with only DFT. Then we can do this very basic machine learning with just a fully connected network. And then we have some crystallographics now with mostly materials project data, and then some other data that was from prototype-based high throughput searches. So diverse in terms of chemistry, but not in terms of crystal structures. Try to, then we are doing a lot of geometry relaxations, and we can retrain our models. So I told you about this first set of around 1 billion. So we do a billion predictions, and then we do around 500,000 geometry relaxations, and we can see the distribution of our validation calculations. So here we have the percentage of compounds that are in distance to the convex hull, and here we have a cumulative percentage in terms of the compounds that are below this distance. So we are validating compounds that are predicted, for example, to be below 50 atom. And then we can see the distribution of the validation calculations. And so we basically don't change anything about our workflow. We just have a few 100 lines of Python notations. And then we have, we just do our predictions and validate. But just through creating all of this data, our model improves significantly, half our error, and through this roughly 1.5 million calculations. And then at the end, we already have around 10% here of the compounds that are very close to thermodynamic stability. So we can, just directly look at the percentage of stable compounds. So now, after these 3 rounds of, think in total predictions in the end, and we're now at 5.4% of the materials being stable. And then with some advances in machine learning, so using the universal force field, additional filtering step in combination with another custom model, and we can get now to 36%. So that in this case, this problem is to some extent solved. If we do a lot of predictions, we can now generate one new stable crystal structure in terms of DFT and with 3 calculations. And here we basically also have the power of more filtering steps and some. So here we use the use some model first to predict the stability. Then we use some universal force field to relax the crystal structure. And then we have another model that predicts the stability. But this model is trained now to map universal force field relaxed crystal structures to the DFT results instead of DFT crystal structures. And so we calculate percentage, and then we have all of these calculations collected in the Alexandria database. And in the end, we have 5 million calculations, but 45,000 stable compounds. Of course, there are quite a few more that are close to the convex hull, but not so many in comparison to the 5 million calculations. And so the majority of these actually never be really interesting in terms of any material science, but they are very important for the machine learning. And so this may be one, consideration that sometimes, even though it might be more efficient if you add some extra physical priors, for example, in terms of oxidation states. First you might miss out on some interesting chemistries that, might go, but then also, you have some extra work and you're creating less data, which is just as important as the rest. And so if we, want to use one examples where the universal force fields were heard about. So one previous, now it's maybe not so important anymore benchmark would be the materials MudBench was about predicting new stable crystal structures using universal force fields. And so around 1 year ago, we had here MetaSim from Microsoft and Genome and then we had some other projects from academia and from startup Orbital Materials. And at the time, the problem was really that the large databases of the company is closed source, and so there were no, academic data sets available. And then using all this geometry relaxation data from the Alexandria database, Orbital Material were then beyond the existing models of the large companies. And so it's just about the importance, of having open data sets and running a lot of calculations. And with Meta, they have been very open about their data sets. They created this OMA data set by running some molecular dynamics and rattling some structures from Alexandria, and a whole sea of new models. Sea of new models. So of course we heard about the Maze models. These are not up to date as this benchmark basically. Who's the best performing one here? But what's maybe interesting to see is here that we have a lot of models, for example, Maze here or Grace that have, I think more or less the same different points in times also. The Equiformer here with the same architectures. And in the end, the performance mostly depends on the data. And so, it's also just maybe there are not so many people creating large data sets. Just to consider that this is often more important than creating a new, and can have a long-term impact also. Yep. So now we can run 5 million DFT calculations, kind of how do we do it, and also how do we do it for more complex workflows. For example, if we want to calculate a critical temperature for a superconductor or something like this. And so I have this quote here, civilization extending the number of operations we can perform without thinking about them. This is slightly out of context of the original meaning, but I think it hits the point pretty well. I'm working in Nicola Spaulding's group now, and she still had to code her own DFT code and get her own pseudo potentials for new material. And of course, this is not the case anymore. We have very real that can do very reliable geometry optimizations. And then we have other codes that we'll see that, built around all of this to do some more complex workflows. And then if we can do them completely without ideally even our holidays, then we can get quite far. And so if we look at the example from Alexandria, this is the super simple workflow. First, the non-magnetic vast relaxation, so no spin up or down. And then we do 2 collinear relaxations in VASP, and then we do another static calculation to obtain a more accurate energy. Of course, there's already some approximation here because you have no guarantee that after, 2 relaxations in VASP, if your cell shape still changed after this relaxation here, still actually I have to do, third relaxation until, your everything is converged and your cell shape actually doesn't change anymore to obtain accurate energy, but some time. And so we stop after 3 relaxations here. And so, we can define this in the concept of a workflow. So you have some reproducible of a series of process steps. So in this case, these various relaxations. And then, so we need some software to define that. And then we need some software to do some automated scheduling. So we have thousands of nodes in parallel, and we don't want to look at, the single calculations. And we don't have to say, okay, first we run one geometry relaxation, then we need to submit the other one once this is finished. So all of this set automatically, and the input file, so the output structure of this will of course be the input structure of this next relaxation, and so all of these have to be transferred automatically. Of course, need some very flexible process steps, so we want to run on the whole periodic table and all possible crystal structures ideally. So they need to be very flexible. For example, when we have the materials plus U settings, we might have different smearing algorithms depending on the band gap that's calculated in one of the first calculations, and so on. I mean, there are calculation recipes in some of the workflow codes that we'll see later. And then, of course, we need some systems to detect errors. This is the most important part, that we don't end up with nonsense data in our database. Databases still have. So, I mean, just if you work for a long time with materials project, Aflow, and also Alexandria, I mean, at some point you will come across something that's, I mean, obviously wrong. If you tell, I mean, the respective people, so in Alexandria case, you could write Miguel or myself, and tell us that there's some nonsense in the database that we should please remove. So there's still systems to detect most of these errors, so hopefully, I mean, there's not too much nonsense. And then, of course, ideally, we also have some systems to recover from the errors. So, I mean, if you have, for example, with geometry, I mean, if you run some VASP calculations, you will commonly come across this errors. So basically, you have some minimization algorithm here, and we try to have some, I mean, a bracket, try to find some minimum inside of this bracket, and I mean, didn't find anything anymore. And so in this case, you have to restart your relaxation, and usually you just, I mean, have to copy your output structure and use it as you know. If you have to do this by hand, it would be super annoying. So of course, you want something that automatically checks your output file for this error, and then does the respective steps and your calculation. And then, of course, we have to store our data somehow and organize it by some form of metadata. And I mean, there are also libraries for that. Yeah, and now in terms of workflow software, so this is in quotation marks. So Alexandria just used some basic Python code and a little bit of Bash. I think it was probably quite a few less lines. I mean, because it's mostly, I mean, about these 4 steps here, and then recovering from some common errors and handling, I mean, all the distribution across thousands of nodes. But you don't need for this. But luckily, there are a lot of people who have done this in a more professional fashion. And so we have, for example, AIDA or Automate and Jobflow, which we are going to take a look at in the tutorial. And for example, is from Germany. And all of these, I mean, frameworks have a lot of variety in terms of workflows. I will show you a few examples in a second. And basically, on high throughput calculations, and you're not using any automated workflows yet, you should definitely consider them. I mean, first, they help a lot with data provenance and reproducibility, also ideally leading towards, I mean, some reproducibility. And then they mainly allow you to access the expert knowledge of other people. So, I mean, if you, for example, have a PhD student, I mean, who figures out how to run value calculations, do some automatic conversions, and then run some BSE, then usually this knowledge gets kind of lost once the PhD student leaves. But if you have some automated work implemented, then you can keep that in the group, and also the rest of the community can access this if you publish it in one of the common frameworks. And so everybody can profit from it, from all the expertise that's accumulated in groups. And luckily, I mean, this is some very recent development, and I haven't tested it out personally. But now there's some software to allow for some interoperability between these. And because usually most groups are kind of fixated on using one, because you need to set up your database infrastructure and, I mean, get people trained in the different workflow management environments. And but this, I mean, development should now allow for you to export some workflows from one workflow management system to another one. So these are all in Python. This is not possible for all types of workflows, but I think for quite a few already. And yeah, so what could we do with these systems? We're going to later use some Automate tools. So we have everything from, for example, workflows for ferroelectric structures. We have the standard workflows, so electronic band structures. But then we also have some more complex ones, for example, doing some quasi-harmonic approximation for phonons, some anharmonic phonons, and we have all the workflows from the materials project. So if you're working with their data and you would like to be compatible with them, you can just use their workflows, and you are guaranteed to be compatible with the materials project. And yes, so we have the introduction during the tutorial. And then we can look, I mean, basically now if we're looking at all of these properties here, for example, we might want to have calculate some electron-phonon coupling for some superconductors and some other quantities. And then we don't have a single optimization problem anymore, but we need to look at some Pareto front of the best materials. So this is just a common concept from some multi-target optimization. I think we'll also have some more examples of this concept during the rest of the lectures here. And so we could have, for example, here our critical temperature for superconductors and then our stability. And basically, we try to find a balance here between our properties. Of course, here now you need the domain knowledge to decide if you actually want the point here on your Pareto front or if you want to be down here. But the main challenge, I mean, still often stays that you need to have a material that's actually feasible. Of course, if you work with known experimental materials, so if you query experimental databases, this is not a problem, and your material will exist. But if you work with theoretical databases, this stays the main problem. Of course, if maybe you're working in a different field of material science and you're working maybe on some metamaterials, then you will have some easy way to determine if your material is feasible to create in your experimental setup. So I mentioned this example here. This is some large high throughput search basically through the whole, inorganic crystal structure space for new superconductors, of course, only conventional superconductors, because we cannot really predict the unconventional ones. And so we can see here, kind of the problem in terms of our Pareto front, that the ones that are actually stable in terms of superconducting are only the ones with a low critical temperature. And then all of these here, are usually hydrides, and maybe there's some possibility to synthesize them at high pressure and potentially stabilize them somehow. But this hasn't really been, experimentally explored, only for the hydrides, at extremely high pressure that, also only stay stable at this high pressure for a short time. And so this will always, be the challenge in the high throughput searches. Now, so far I mainly had this prototype-based generation of crystal structures. So we'll look at some few other opportunities, how or ideas how we can generate our materials library to do our high throughput searches. So maybe the most sensible one often, I would say, would be this experimentally known one. So you can query your experimental database of choice. So in this case, we're looking for new two-dimensional compounds, and Nicola Mazzari's group looked for some suitable 3D compounds in the experimental databases, and then try to identify these low-dimensional subunits here. And then you can use the DFT, calculate the relaxed geometry and the binding energies, and then you have some potential new 2D structures. And of course, this has the advantage, you know the 3D structure exists, and ideally from some experimental paper how to synthesize it. And then the only thing you have to worry about is the exfoliation. Now, we went in a different direction. So we just considered we have 2D materials. There are a certain number of space groups in 2D. We can generate all the Wyckoff positions, fill them up with random coordinates, and then again consider some arbitrary combination of elements and generate a huge space of materials. Now, in principle, in this way, we could enumerate through all possible symmetry times element combinations. But of course, then this will be very expensive. And so you have to use a lot of physical priors here that introduce a lot of biases in terms of, historical chemistry knowledge, and to actually remove a lot of the compounds we generate. And then we'll use some more filtering steps here. So this was some of the, first universal force fields, I think. Just some, when Magnate came out, just transfer learning some magnet on some few thousand geometry relaxations from here. And then we can see already which structures or new prototype structures actually relax into the same prototype, so we don't have to run the duplicate DFT calculations. And of course, at the end, we end up with our convex hull. And so, this generates some very fun prototypes that are nice to look at and might be interesting for experiment, but we really don't know because the 3D counterparts don't necessarily exist. And we also, don't necessarily know if exfoliation will be possible. So this is basically always the difference if you work with experimental versus theoretical crystal structures to start from. And then we have the third and a little bit newer approach, which is very popular now. We can also just directly use some generative models. So we'll have a few more lectures about generative modeling here. So we'll not go into any details here, but we can use, for example, some diffusion models. And then, of course, we need to define an element space as well. But besides that, the only bias we have now is a data-driven bias. And in principle, if we have, of course, a model that's sufficiently well trained, this should be more efficient because we can, in latent space, bias towards the properties and the stability that we want. But it remains very challenging to generate synthesizable crystal structures and stable ones. And so, this also mainly, or the quality of this in the end mainly depends on how good your universal force field in the end is, or the respective model that's usually quite similar to universal force field in the end that gives you some stability of this crystal structure inside of your generative approach. And then, of course, these are just the starting points usually. So usually you can use some global optimization strategies. So I think we'll hear something about Bayesian optimization. We can also use evolutionary algorithms or all kinds of other global optimization algorithms to go from some starting library to sampling some more efficient structures in the very end. How much time do I have left? 10 minutes? Okay, perfect. So some practical considerations. So this was just some basic, overview of the concepts that we typically use in high throughput search. And I thought it might be interesting for some people here what we have to consider in practice. So one part is licensing. So all the data that is published, and that you might access in terms of databases has a license associated with it. And so your typical license, from academic projects like the materials project, is a CC BY license. And then this allows for some rather broad reuse. And the main thing is that you have to, appropriately cite them and, tell everybody where your data comes from. Now, of course, just a disclaimer, I am not a lawyer or anybody, and so don't rely on anything I say. But still maybe something useful in here. Then we have the non-commercial licenses. For example, the Genome Project by Google. So they published them in few 100,000 stable crystal structures, but they are on a non-commercial license. And so, for example, if you take this data and just validate your machine learning model that you didn't even train on this data, on the genome data, and then later use this to predict some new material or predict some material property, and then do some DFT calculations on this, and then you publish it on, for example, on the Materials Cloud, and you put the normal CC BY license there, then you're breaking their license. Because any derivative works of the non-commercial licenses also have to have a non-commercial license. So this is, this is important. So just be aware of this. For example, if you're working with the genome data, it's great that this data exists, but basically, if any of your work comes in contact with it, in principle, you should not publish it under an open license. Now, of course, this whole part is quite funny because all of the big AI companies right now have their large language models that are all trained most likely on a ton of licensed data and copyrighted data. And these cases are all in court right now. But usually we don't have the resource in academia to deal with these lawsuits. So. And then we have the commercial databases. Now, of course, these all have their specific license agreements, but just be aware that, usually these license agreements do not cover any data mining or training ML models on them. So, for example, this again depends very much on the license you have and on the database you're accessing. But if we're talking, for example, in terms of ICSD, you are not, as far as I understand it, not really allowed to train a machine learning model on this data and then generate a new database on it, because you're not generally allowed to generate new databases based on the ICSD data. And so just something to consider if you go into the high throughput space, just check what the commercial data you're using says about data mining and ML models. And then, of course, we have some worldwide variations. So, for example, we have some European database directive. And so even if you collect some non-copyrightable data in the European Union, you will still gain some rights in terms of what other people are allowed to do with your database. But then if you would do this in the US, I think this is not the case. So just keep this in mind when you start with your projects. And then, of course, we need our HPC resources. So I think, just some rough estimate would be that the whole, Alexandria's maybe in the end like 200 million core hours or something like this. And of course, we do not have this in our local supercomputers. So, there are some national supercomputing resources, these vary heavily by country, how much resources you can access there. And then we have our shared European supercomputing infrastructure, the Euro HPC joint undertaking. You have all the systems, not all of these are operable yet. But you can, check them out online and see what kind of system they have, so how many GPUs, what type of GPUs. For example, maybe you cannot run your code on AMD GPUs yet or on Intel GPUs. And maybe then also talk to some other people. Some of the newer systems, when they come online, they might not be stable yet, but maybe they're empty, so there are always some advantages and disadvantages. And then just a recommendation, if possible, you can apply to multiple supercomputing centers. Of course, you need to use different projects. You cannot obtain, duplicate funding, but there are some, usually some national supercomputing centers where maybe you can apply to some smaller and larger ones. And then also you can collaborate with companies. And so, of course, often companies will not allow you to publish all of your data, but maybe they will only want to keep the most interesting candidates secret, and you can publish all the rest, and they might give you a lot of computing time. So this could also be an option to obtain your computing time. Now, the process is quite simple. You just apply for benchmark access, which you usually can do, continuously. You run your benchmarks, figure out what's the smallest node number that you can use to run your calculation types. It's important that you minimize the communication overhead so you're as efficient as possible. And then, you can apply for a regular or extreme scale allocations, which, usually, every few months, you can, there's some new call. And then some quite random recommendations. So just be aware of your local resources. So if you have a single 64-core processor, you have 500,000 core hours a year. You just need to use it 24/7. So if you don't use it while you're on holiday or during weekends, then you lose around 250,000 core hours. So just be aware of the local computing resource, especially. Maybe there's some old computers lying around that nobody's really using anymore. These might give you, over, for example, the time of your PhD, maybe like 5 million core hours, which can make a huge difference. But of course, I'm not telling anybody here to work during the weekends or on holidays, so automation is key. And also, usually if you try to set up these kind of jobs like a few hours before you're leaving on holiday, something will go wrong. So it has to start a little bit early to make them work. And then maybe some other recommendations. Supercomputing systems are usually empty during Christmas and New Year's Eve. So I think 2 years ago, I could run, I think gain like 12 million core hours on CSCS systems during just a few days. And if you set up your computation ahead of time, you have your holiday, but you also have your computing time. And then maybe you have some low priority queue or some preemptible jobs or spot price kind of type of system where you can also gain maybe like 30%, or in some systems you might gain, unlimited amounts just in terms of how many people are not using their time. I hope this was useful for some of you. And then I'd like to thank all of the people and, of course, the supercomputing centers helped us. And Miguel March, with whom I did my PhD, and we'll continue to work on the Alexandria database and the materials theory group, and Nicholas Spalding at ETH. Thank you.
We can have a few questions from the audience. Yes.
Thank you. You mentioned kinetic and synthesizability metrics. I was wondering if there was any way to calculate those in like a high throughput manner as well, or computationally.
Yes, so, there's some work, for example, from Christine Person's group that at least goes in this direction. In terms, but this is more in terms of calculating, for example, which precursors are likely work and what are maybe the energy barriers between these and calculating reaction networks. Now, of course, if we would like, true kinetic information, you would basically have to run whatever process you want to run, one-to-one in terms of a simulation. I would say, if you, of course, there are approximations that you can do and where you get closer or further away from the reality. But so I think this is very much challenging. And my hope in terms of this is just for experimental high throughput. So, the more automation we get there, then I think it will be cheaper to run the experiment than actually trying to figure out 100% for a specific compound if you could synthesize it or not.
So there wouldn't be so much use in integrating that in like a materials discovery workflow, like adding specific metrics for those things wouldn't be so useful. It'd be more towards the application stage.
I think, like, for example, the reaction networks, etc., I think these are very useful. And then the other ones just depend on the cost of your calculations versus the cost of running the experiment. And
Thank you.
Will be like a personal resource question. And then also if you find figure out some smart, predictors that you can relate to experiment. But the problem is that we are lacking all of the negative data in terms of experiments. And so, right now, people are slowly starting to produce this and trying to extract this data from the literature, but we just don't know enough about it yet, basically.
Other questions? Yes.
First of all, thank you for the nice talk. So I would just ask you about the electron-phonon coupling through the high throughput. How is possible to, let's say, going step by step to calculate in a more, in a deeper way the electron-phonon coupling? So, for example, you have thousands of structure. So how can you simplify the calculation of electron-phonon coupling until a certain point? It's not so clear in that sense. Can you?
Yeah, I can
Thank you.
say a little bit about this. You should, if you have want some details, you should probably, I'll talk to Miguel Marx or Antonio Sana, but the basic points, first, of course, we usually reduce our data set to some more high symmetry structures, which of course reduces the costs of everything. Then you do your phonon calculation, and you'll find that a lot of the structures are not actually dynamically stable. And then you can use different grids in terms of your electron-phonon coupling calculation to keep the cost at a reasonable level. Usually using quantum espresso in this case. And so going from different grid sizes. But of course then you will miss certain things. For example, MGB2 you will not get correct, basically with the high throughput approach we're using. So there's some, and then of course once you have the interesting candidates, you can run your anharmonic phonons at temperature if you want, and see if these, renormalize your phonon coupling, and probably find out. And then then you can do a lot more detailed steps again if you want. But this is the basic idea.
Okay. Thank you so much.
Other questions? Maybe I have one. It's about the knowledge barrier that you must have. Suppose I'm a first-year student and I want to start doing all these things. Do you think that the barrier is more, the knowledge barrier is more towards the codes that you have to use, or towards, say, like the physics as well? Because in a sense, in order to make smart choices for the workflows, you also need to know what you are doing. So what do you think? Also in the light of having some workflows that can be also used by other people.
Yeah. So we'll see. We'll see the Atomate, for example, which has all the materials project workflows integrated. So in principle, a first-year student could use these and have all the knowledge that was used to create them. This, let's say, Materials Explorer part of the materials project. But then, I found that, often the barriers are a little bit in terms of the experience in running the calculations and keeping everything organized and basically don't make any mistakes, because once you submit, a job to 1,000 nodes maybe, and then, you use a significant amount of computation time, you want to be very sure that everything is correct that you're doing. And so maybe this experience there, but then, so it's usually, good that if projects scale up slowly from, some process of a few thousand calculations to, then at some point, some million calculations. This, I think, the important part. And yes, then, of course, in terms of knowing when a workflow will be wrong, this is, where there's some knowledge about the materials is required, and also understanding of how the workflow was created. And but there are, of course, you have the supervisors and the other people in the community who can help with that.
And how much do the supervisors need to be knowledge?
Well, in my case, the supervisor has had all the knowledge and the skills to run the calculation, and then have the machine learning. So this kind of depends, I guess, what the job will be. So I think Christine Persnater said in one talk, she always lets all the people create their own data before they're allowed to do some machine learning. So then you will gain the knowledge quickly, and maybe in other groups you will first start with the machine learning and then gain the knowledge.
Thank you. If there are no more questions, we go ahead. What do we now? Yeah. Tutorials.
Yes. Let me just quickly change my screen.
I don't know if you want to keep using the Microsoft.
I will keep trying to use the So, is this properly visible? From the back in terms of size? No. No. Okay, let's see.
Like this, I think
this should be fine. Okay. So there will be also two tutorials here. One focused on, looking actually at what databases we have available and how we can obtain the data to start our high throughput searches. And then the other one will focus on using the automated workflows. Now, I know there are some people here who cannot actually, access the servers we are hosting the tutorials on, which in this case, for the second tutorial, there's unfortunately no way to work around this, because we'll use some database, hosted on the local systems here, to submit workflows to and then to retrieve the result from. And so, in this case, you have to ideally find somebody, else to work with. Okay, so we can take a look at this. Now, this is also something where you can, I will try to go through this and just say some important words here about these, and then you can read through everything later in Intel. And also there are some exercises in the end of each notebook that are more a bit of an inspiration for you if you're interested to explore some different tasks and check how much you already understood and how you can, and maybe some ideas for learning a little bit more. Now, the idea of these notebooks is that we're looking for some new garnet structure. So there's the yttrium iron garnet, which is used in spintronics applications, or people would very much like to use it. But there is some materials problem there that we don't, or we can only really create clean crystal structures or thin films of the YIG on top of another garnet substrate. And we don't really have a good substrate that is metallic, or at least has a very small band gap, so we can use it probably for the spintronic application. And so there's a real material science problem that, to my knowledge, also hasn't been solved yet. So if you find some interesting crystal structures, you might want to check them out. Now, so we already discussed these concepts here. So, our ideal substrate should be thermodynamically stable. Then it should be reasonably safe to work with. So, experimental colleagues will become very annoyed if you come to them and ask them to work with some plutonium. So please don't do that. And then we want it lattice matched the YIG. So we'll look at the lattice constants. So we can create, ideally, find a material where we have very little strain when we grow the YIG. And then, as I said, it should be metallic or have a small band gap, so we can have some conduction for some applications. And now the idea will be that first we look in some databases. And problem is, of course, there are a lot of databases, but there's one, direction to try to solve this in terms of creating a common interface or API to all of these databases. And so this is called Optimate, and we're going to use this common API to create a few databases, and then use these as a starting point for our high throughput search. And then later on, I will discuss this in the next notebook again. We're going to use Atomate 2 to relax some new crystal structures and then evaluate the dynamic stability. And yeah, so about Optimate, you already might know some of these databases I mentioned: Materials Project, Alexandria, Airflow, OQMD, Nomad. We have the Materials Cloud, which also has a lot of things collected. So of course, Nomad also has data from other databases collected, so there's some overlap. And basically, all of these originally had their own API. On the case of Alexandria, it didn't have any API. And Optimate basically solved this problem, so all the database providers came together and over long discussions agreed on some common standard, what is supposed to be crystal structure. How we can define this in terms of a computer interface. And now you can use the cell database and obtain results from all of these together. And so basically, what we'll use is this Optimate client. And so this will build connections to all the different databases. And so if we initialize it without any extra parameter, it will be initialized, to look for all the 27 databases. I think we can look at these here. So we have a list of all the databases here and some, short name for the provider, and then there are usually some URLs. If you click, I would continue here, and then there are also full details for the provider in terms of information, what they actually provide. And so this would be a problem. So if we could run this query here, and then we would be looking through 59 million crystal structures, and we would probably not be finished, until maybe dinner today. I'm not sure, depending. Some of the databases are faster, some of them are slower. And so we're not going to do that, but we are just going to pick out two specific databases here, so OQMD and Alexandria. And then we can define our client here and ask for some crystal structures down. And so we'll set the max results per provider here. First, I don't want us, 60 people asking all the databases for a lot of data at the same time, which I'm not sure if they will be able to handle it. And we also not need so much data here. So we can run this code to initialize everything, and then we can take a look at what kind of properties these databases actually provide. Okay, now we got this error, so I tried to run this in the morning, and there OQMD is fine, and now it has some problem again. And so let me quickly fix this. Just see what happens if I take this out. So sometimes some of the providers are not available. And this just happens, and there seems to be some instability, with OQMD over the last weeks. But we can just take a look at Alexandria here. And you'll see we have some COM types here. So we'll have some ID that every crystal structure database has. We have the elements, the chemical formula, and all these, kind of base information, lattice vectors, Cartesian sites. So anything that we can build the crystal structure from. And then we have these types here. So in case of Alexandria, there will be some Alexandria in front, OQMD, OQMD, and so these are database-specific types. So we cannot query OQMD, of course, for Alexandria bandgaps, or the other way around. But if there are COM types like bandgap, we could query all of them, asking just for, either Alexandria or OQMD or Materials Project properties. Now, one important thing to consider is, of course, that all these databases, use different calculation protocols. So while we have a common interface, the data they provide in terms of density functional theory will not be consistent. So one, has to be aware of this, and no kind of, Materials Project and Alexandria are mostly compatible. And so, for example, these you could more use together. And so now we would like to, query the databases for YIG to find the respective crystal structure. Now we can run this and see what happens. And so it's performing the query here. Now, I can tell you the results. So the issue is that YIG is actually not in Alexandria, but it's in OQMD. And so if OQMD is unavailable right now for some reason, then we will not get any actual crystal structure out. But we can still look at the format of the responses, and we have the crystal structure saved. In case of this happens, and so we can continue using just the saved crystal structure. And so if we look at the format of the structure, we'll see here already, we can look first, I guess, at the filter. So everything is defined basically in terms of some URL that defines the query. And so we're querying the structures endpoint, which is basically where the databases provide this information of structures, about structures. Then we have here our query. So if you run multiple queries, you will find that the client, caches these different queries, and so you can access them in a dictionary form. And then we will have here the replies by the different providers. So for example, by OQMD here. And if we would look at the full format of these, then there's also some meta key that provides some meta information. So from what was your query, how many data points did you actually obtain from the query, how many data points are available total in the database, and if there's more data available. So we limited our responses in the beginning, and so we'll see if there's more data available or not if we ask for this. And then, depending on what we're looking for example, we might only be looking at the band gap, then we would only ask for the band gap, and everything would become quite a bit faster. So we could define a set of response fields here. And now, as we want to find the correct iron garnet crystal structure that we can then match our lattice to, we could query for the OQMD for the stable structure. So there is some OQMD stability keyword, and we can just set it to 0 in our query, and then we should get the respective response, assuming OQMD would answer at the moment. I will just try again to add it to the client and see what happens. So this looks good, so we can try again. Yes, so now you can see that similar to Alexandria, here you have the different keywords with the OQMD names, and OQMD also has an ICSD ID. So they have tried to match structures to ICSD, so you can, based on this, identify the corresponding experimental structure. Though these are not always, 100% correct in the databases. So if this is important for you, you should also check by hand usually. Okay, so usually, if this, basic query takes a lot of time, this means probably there's the problem again with OQMD, but we'll see. And basically the next steps we would do would be to, filter the compounds we obtain, find the thermodynamically stable one, and then we could can look at the different attributes of this. So we'll get an entry ID, so a unique identifier in the respective database, get the ICSD ID in this case. We can obtain the distance to the convex hull. We can obtain the space group, so we know if it has the correct symmetry that we're expecting, or maybe we would want to find out what symmetry it has. Yeah, so there was this problem again, basically. So just try to rerun this with OQMD later. Usually, in the morning it worked, and so it, changes might change depending on time always. And then we could now look through both Alexandria and OQMD to try to find all the structures that correspond to garnet. So we can, for example, look for the chemical formula in an anonymous form. So this basically corresponds to this prototype-based strategy that we did before. We just said, okay, it should be in this case A12E5C3 for garnet, and then we can confirm the space group is the correct one, and then we are quite likely to have the correct structures. Now, a lot of databases also have some prototypes defined so that you could, try to find it and then, for example, check what's the prototype. Usually it will be some number or composition with a number, that is the prototype name. And you could try to query for all other structures with the same prototype. And yeah, so we'll run this and then we would obtain some responses. And so in this case here, we'll mainly get data from Alexandria. So you can just see. Now this will take a second, and basically in this you will see that Alexandria will tell us that we will require some, or that it has more data available. So I think it should be in total around 15,000 different garnet structures that would be available. This would also take, a few minutes to download these, and so we have already, downloaded them and provided them as data, that you can then just have a look at. And yeah, sorry. So this part here, I think we're just taking a second again now running this because it's first trying to query the OQMD, which is not responding. So in your client, you can set, for example, this timeout, and where if in this time you don't receive proper response, then it will stop. Or you can set a maximum number of tries so that you try to query data. Do repeat the respective query again until you receive a response a certain amount of time. And then we can, load the data that we have already downloaded. So these 15,000 structures, and the first YIG structure here. And so we can do that just in terms of building some PyMatchn structure. Or we can also, just use the classes that are available inside of Optimate that just allow us to convert the structure format in Optimate, for example, directly to PyMatchn or ASE structures. And so in this case, we'll also use the Alexandria energy and the bandgap and hull disk. So later on, we could, for example, train some machine learning models on these quantities here. And so yeah, we'll just interrupt this now. So you should, just commenting this this part here out, and the rest, the Alexandria should run quite fast. Let's really just load this data here and convert it into the format. And can take a look at it. So often, as I said, we want to look at the distribution of data we have. And in the past, it has been quite a challenge to make some nice periodic table plots. By now, there exist some nice libraries. So, for example, this PyMatWisp by János Riebezel, that allows us to very easily create some nice, just some warnings. And then we can see the periodic table. And so here, we can basically see how many garnet crystal structures we found in the database based on our query. That have a respective element. But of course, we didn't do any filtering here yet. We just know that these are garnets. So we see, of course, a lot of oxides, sulfides, selenites, tellurides, etc., which makes sense. Just based on the oxidation states that the sulfides also work out, based on the oxides that we know. And now we can, apply our materials funnel. So we can, look for the band gap, the distance to the convex hull, and lattice constant. So in this case, we convert to conventional structure. So we have a consistent definition of our lattice constant. And then we could run this filtering here, filtering procedure. And so running this for the whole data sets also takes a little bit of time, just based on, having to obtain the conventional standard structure. And so just quickly load this filtered data here. And then we can have a look at the plot for the filtered data, so candidate crystal structures for our high throughput search, so potential structures where we want to calculate maybe some more information with a higher quality functional now to check is the PBE band gap is often nonsense, so maybe we want to do some MBJ and see what the band gaps are there, or relax it with some scan. to obtain some more accurate results. And so here we see we actually have a lot of nitride garnets that are that seem to be the most likely let's say the most likely type of garnet to obtain some interesting candidates. And next work notebook we will focus on trying to scan through all the nitride garnets using automated workflows and see if we can find any more interest structures. Now, of course, we could, also explore the whole garnet space, but these structures in the end are quite large. With machine learning models, we could do it with DFT and would be a bit expanded with the 80 atoms in the unit cell. And then, so I will just quickly go through the notebooks, and then, there are some exercises here, so you can first explore all the queries, in relaxed manner, and then some ideas, so you could try to incorporate, for example, the filtering criteria we used in the end directly in TMate query, and try to only download the data that actually interests us in terms of materials. And you could also use the client's callback feature, where you can add some function directly applied to the data you queried for. To do this, there's some different ways you can do it. And then you could explore some more of the visualization features of the PyMart. For example, you could try to plot the distance to the convex hull. Okay, this would be another task here. You could, for example, try to plot the distance to the convex hull for all the garnets containing a certain element. So you could have a distribution plot or histogram inside of your periodic table, inside of each panel of the periodic table. Or you could try to split up each panels in the periodic table and have a separate panel for the ABC, so the A3, B5, MC12. So we actually know that these are garnets or the nitride garnets are actually with N12 and not maybe with with N3 instead. Yeah, so this would be, the basics about the Optinate. So, depending on maybe a few more words here, depending on your application, you can set some experimental databases. Now, also just, beware of the licenses. So, for example, here we have COD and not ICSD because it's under closed license. I think there might be access to the genome data as well. So there, of course, you would also have to consider the license issue. And yeah, so now the idea is that we do a prototype-based high throughput search, and so we'll do this in a collaborative fashion because we cannot run each a few thousand geometry relaxations now, even using the universal fields. And so we'll have a common database that we all submit our workflows to, and everybody runs their own calculations, and then in the end we can see what we accumulate in terms of structures. You can also run them after the tutorial is finished still, and we can see later on, during the conference, what structures were found. And so there is a certain setup required here in terms of the environment variables. So basically, I will go over what, Atomate and JobFlow are again a little bit, what their specific roles are. But basically, we have to set some environment variables that say what's the IP of our database. Now, did you post this already? Yeah. So your notebook will have just written some quotation marks IP address, and so you can enter this IP address. Of course, now this part will only work, I think, keep working while we're running the tutorials here over the weekend, and afterwards the database will probably be shut. Yeah. And then, so these will then automatically set some environment variables. Once we run the calculations, we'll do one more setup script, but I will explain it then. And yeah, so how does the Atomate part work? So there was also recently an Atomate school that has detailed talks about everything, so which I can recommend if you're interested in using it. But basically, there's this map here where we'll have Magna. So this is quite modular for the databases and the storage abstraction. So we are mainly using Mongo databases here. Now, of course, these have a limit in terms of the size of objects that they can direct. And so we'll have some separate stores for some other data types. Then we'll have JobFlow, which will be our, workflow engine. So just defining, the subsequent steps, analyzing all of that. most of you will probably already be familiar with PyMagine, which just, has an incredible amount of tools in Python tools in terms of material science for analysis, but also just the classes we need to store certain objects. Then we'll have Emmet, and this is responsible for the data schema, so just defining what should be the output of a relaxation calculation, what should be the output of a band structure calculation, and then storing these in a database. We'll have Custodian, and this is also useful even if you do not, use any automated workflows. In the end, you could just use this to run a lot of, electronic structure codes just on its own, and it will do some auto error correction and validation of your calculations. So this I can, just recommend even without using Automate. And then of course, Automate has then the specific calculation recipes defined. So, there's just some most basic example from JobFlow. So the idea is that our atomic units are jobs. And so, for example, we can take a basic Python and just use this add job decorator. And then we have a job defined. And then we can, for example, connect that with a second job. And then we have a flow, so 2 jobs that will be executed subsequently. So kind of the very basic idea. Now the point is when we define this object here, we are not actually executing the jobs yet. But we can draw a graph here that tells us a little bit about our workflow, and so it's a nice way to get an idea of some more complex workflow actually being done. And it might be easier to understand in the beginning than just going through the modular Python code where parts of it might be in PyMagine and parts in Automate too. So, and we'll later take a look at some more at the Phonon workflow, which will be a little bit more complicated. Now the point here is we have this error here, and so the output of first edition here, of course, is used as an input for our second edition, and so this is shown in the graph. And if we execute this job, and we can either run it locally or we could run some HPC resources, then the jobs will be run in the respective order. And yeah, so we run them locally here. And so it informs us about the jobs that are run. They have some specific ID. And then we obtain our final result here. Now, these first in some local or memory store. So this would be gone once we close everything. But normally we use some Mongo database where all this information is stored automatically if we initialize the store. And so beyond the job flow, which is responsible, for defining the workflows and something to connect to our HPC resources. Now there is some job flow remote in development, and it's in beta right now. You can try to use it, but for now, I use the Fireworks. It's kind of was used as a predecessor with Automate 1 instead of job flow, and so this basically allows us to convert our job flows to workflows in Fireworks. It's a bit, of course, annoying that we have the very similar names, but everything else in Fireworks is Fireworks themed, so the jobs there are Fireworks. And so to submit them to our database where they will be stored, we will launch, so we will add these Fireworks to the Launchpad, and then they will sit in the Launchpad and be ready to launch. And then you can go to your HPC resources, which in this case will go to the terminal, and then there we can check which workflows are ready, and we can then launch them. This will change the state of these workflows, which you will be able to see. In terms, if you use some command to check the states, and then will either complete at some point, or they will fizzle if the Fireworks. Firework didn't really explode in the. I guess didn't work out in the end. Then we can query the database again and see what was the output, and then we can analyze the data that we obtained. And so here we have this basic example from above again. And so now you can see we just added this to our database. And if we go to some terminal, check. So we needed to set some environment variables here again, but I put this script later on, but this script here, activates the environment, sets the variables, and also then starts launching jobs. To this in a moment, so for now we'll just use this here, set the environment variables, and then check which jobs are available in the database. So we can see here, so the last job here fizzled, so it didn't run correctly. We have another add job here waiting, and I see a lot more add jobs from other people tutorial here, I assume. And then there were some previous test calculations that were run to check that the universal force field that we run work fine later. And you will also be already to query for these results here, and before we add more of our own. And so if you try to run this work launch command, of course, this workflow here was only defined, within here, and it's not actually defined within Atomate. So this is a completely separate process. Now to find this workflow, somewhere. And so, it's not just running with our launch. But yeah, so once these workflows are submitted, in principle, we can just use some different tools to launch them. So we have QLaunch, where we have some setup, usually for Sloan's queue or whatever queuing system your cluster is using, where you can define, how many nodes we're using, what should be some environment variables that are set, and these kind of things. And then we can just say, for example, okay, we want to keep 100 jobs running constantly in the queue, and then we can set that, and it will just constantly keep 500 jobs in the queue. Now, sometimes you make a little bit more or easy adaptability, because now here would have to change your some setup file for your Sloan queue, and basically, or it's called my queue adapter, to change your number of nodes. And if we just run some normal submission script in Sloan and then use this rlaunch command here, then we can just always specify node and other settings we would like. Now you can see here that we have here some this -w and then path to my specific worker file. And so right this tutorial, we asked you later on to set a specific worker name that corresponds, to you. And so basically by saying rlaunch and specific worker, you will only run jobs that you submitted to the database with this specific worker name. And so this is useful in HPC systems, for example, where you might use different settings for different types of jobs. You can also have, for example, different worker for different HPC systems if you have different ones that you're accessing. Or in this case, working collaboratively with other students or other people in the same database, you can this way just make sure that you're not accidentally running some jobs for which you don't even have the software and stuff. And yeah, so this was the basics of how we're going to run these jobs later on. Then I mentioned the custodian here will not use, it will be used in some extent in the background, but it's mostly useful for DFT calculations. And then we can go directly to our high throughput search. So the idea is we can load the conventional crystal structure that we got from OQMD before, and then we can check which compositions in terms of nitride garnets we already had available, or we already had that we don't have to calculate anymore. And then we can generate a set of maybe non-radioactive elements. Maybe you would like to remove some more toxic ones here, which you could try later on. And then we generate all of these geometries. Oops, sorry, I'm in the wrong order. So we're generating the crystal structures. And then the idea will be that you set your specific worker name here. So, I had some test worker before. And then we can submit some random ones of these to this everybody. And then you can query, if you would like, you could query for only the calculations that you run, but the default query will be for all calculations in the database. So this will set the configuration file for the my worker correctly, and then here we'll actually use our workflow. In this case, we'll also use the Maze MP force field, as we already used it in the other tutorial. And so we'll have some force field relax maker. And so in Atomate, we have all kinds of maker classes, and these are basically responsible for creating different flows, or also only single jobs. In this case, it's only one job that we are creating. And so we'll have one maker to run a force field relaxation. We'll have a different maker to run a VASP relaxation, or relaxation in Abinit, or quite a few other structure codes. And for the force field relax maker, the main parameter, what we have to specify is which force field do we want to run. So we have different universal force fields available, or if you have your own force field train that's ASE interface, you can basically use that directly as well without any further work. Now in this case, with the Maze MP0 here, we want symmetry, just to make sure that with the DFT relaxation, we always know that we'll keep the same symmetry. With the force field, this is not necessarily the case. We want to fix the symmetry. And then we'll add some extra information. So we will update our worker name. So then the database will know that we only want to run it with this worker. Some extra metadata information. And also update this metadata. And so in the similar fashion here in the other tutorials for Atomate, we'll see you can, for example, also up your electronic structure code parameters if you're not, if you think you need something different than the default workflow, which is probably the case. And then we'll convert again our flow job to the fireworks workflow and add it to our Launchpad. So now check here, and I assume that as if other people were running this, we'll have a lot of jobs right now that are ready. And so before, we had this was in the Jupyter notebook. I'm not sure how's the situation there. Will it be in? It's not there anymore. Okay, yeah. So if you pull it this morning, you will not see this anymore. And so now you could run the launch script that you have to start actually running these calculations. And so what we'll again export your environment variables, and then it will query the database for calculations with your worker, and then it will just start running them. You can have a look at the output, what it's saying. Yep. So now we have a few hundred calculations ready here already. And now we could start running them. So the rapid fire here just says that it should just start running calculations and only stop basically. Normally, if you would submit it to a queue, it would stop once it runs out of time or nothing is available anymore. So in this case, it will only stop once nothing is available. And so here in terms of output, the main or important parts are here it's loading a specific works ID. So you could set a specific priority to a certain ID, else it will just take the last one that we submitted and then create a directory where it will run this job. Now, force fields, we don't need many input or output files. We'll just have some JSON giving some metadata information mostly about the job. Because with DFT code, it would create all the input and then we'd also see all the output files. And yeah, so it already finished the first jobs, and now this will just run in the background. And now we connect to our database, and we could start querying for jobs. Let's see if we have anything here. You can see we already have 81 jobs that are finished and computed. And so because I just set something up in terms of randomly, or some random IDs, And we're just filtering here to make sure that we don't have any duplicates in the end. And then we are querying for, so when we query here, we only query for specific output. Now this, I think, usually takes a little bit of getting used to. So, I mean, all the data is stored in a JSON format. And so you need a little bit of trial and error maybe, or just in terms of figuring out under which keys, which information is stored. Of course, there's some, I mean, you can gain this information from the code. Some of it is in tutorials, but then some also just takes a little bit of experience. So we can run this again. So we already have 89 jobs finished now. And so now the idea is we have an energy from the force fields. How much time do we have left? We're already overrunning? Yeah, sure. Sure, then we'll just quickly go through this. So the idea will be we calculate the convex hull or distance to the convex hull, but obtain all the other points in our phase diagram. We can gain them from materials project. We have to apply some different corrections based on yes, okay, yeah. So I'll do this, and we can later. So for this, we have to obtain an API key. Was just used to having the API key set in my notebook. If you either you already have a profile or you can set one, then you can obtain this API key and quickly query the materials project, calculate the distances to the convex hull. Then we repeat our filtering again, and after doing our filtering, we will be able to run a phone-on workflow. So if we, to obtain the dynamic stability, checking are we actually in a local minimum, are the second how do the second derivatives look? And so this workflow will be a little bit more complex. We have to do a relaxation. We'll determine the number of displaced structures we have to calculate based on the symmetry. In the end, accumulate all of this data to use PhonoPy again to calculate the phonon band structure and see if we have any imaginary modes in the structure. And then, so this is just the setup to repeat. Here we'll have to set, I mean, we have a lot of different calculators here for the different calculation steps where we each have to set the parameters. And you can just maybe run this, I guess, after the session. We'll be able to plot the phonon band structure. And then there are a few more sizes in the back here where you could, for example, also query Alexandria for the thermodynamic stability data, see what happens if you do that with Optimate, and explore a few options. And there should also be some code here somewhere that will tell us who found the most stable crystal structure. Okay, thank you.
You're here until the end of the... So Jonathan will be here until the end of the conference. I really suggest and encourage you to try and run these notebooks by yourself to do the exercises and maybe to convene at some point or ask some questions directly to Jonathan. It's really a good opportunity to have people like you here to help you in the development. The same also, of course, also for the other people the other speakers who had tutorials, exploit this thing.
Good. Thank you, Jonathan, again. So now it's time for lunch. I will lead you on Slack the exact location. So everyone should get some kind of coupon for the lunch. I will lock where everyone exits. I will lock the door so you can leave all the stuff here. And yeah, see you after lunch, I guess.
Okay, we can start now. So in this session, we will welcome several invited talks. First of them is Maria Radova from University of Warwick, and she will present her work on fine-tuning foundation models with frozen transfer learning. So please.
Thank you very much, Katerina. Hi, everyone. Hope you're enjoying the sea and the nice weather. My name is Maria. I'm from the University of Warwick, and I'm supervised by Albert Bartok Bartai and Einhard Maurer. And today I would like to tell you, continuing on the power foundation models, about a different flavor of fine-tuning, which is frozen transfer. One thing I should mention is initially the plan was to show you the performance of the newest foundation models, so OMAT and MPA, but sadly I didn't get the permission from my collaborators because they haven't published the preprint yet. Please work. Okay. Sorry, we literally froze, and it's not a pun. I swear, maybe I'm doing something wrong. And that's it. Apologies for that. The idea behind frozen transfer learning, it would like to have a fine-tuned potential that would rival the from-scratch trained potential accuracy-wise, but trained on significantly less data. And we are not concerned with a transferability. So meaning we will drop some channels in the model, so they will be a forgetting. So we're only keeping the memory of the elements that you're training on. And also we would like to run fast and accurate, robust, stable, and cheap. And we do this by creating an ACE surrogate model, which I'm going to talk about in a minute. So frozen transfer learning is really an industry standard approach, is really popular in computer vision and natural language processing. On your right, you can see the example with the from-scratch model trained on dataset containing cars, trucks, bicycles, so just direct learning data. And at the bottom, we just take a pre-trained model. We are benefiting from its lower level features. We're showing it some new data in sparse quantity, and we're getting the classifier that we want. I should mention this foundation model is trained on cats and dogs, and we eventually get a classifier which distinguishes cars and trucks. So that's the principle of transfer learning. So MACE-Freeze is just a patch for transfer learning for MACE. There is no change of architecture, and essentially it allows the user to set the number of layers or parameter groups that you would like to freeze, meaning only the active parameters get updated. So again, we are starting from the pre-trained low-level features here, and it's very interesting what I'm going to show you next, how this applies to OMAT MPA. All of the examples here, by the way, are based on the first generation MP0. Right. So, and also the potential can be used as a first principle method. So think about it as a free DFT. Again, I will elaborate on this. So this is our workflow. I'd like to draw your attention to subplot B, which is just a schematic representation of the MP0 architecture. So when I say layers, I do the message passing iterations. I mean in PyTorch terms. And it's not quite representative of the actual architecture. This is like just the sequence by which we freeze the blocks. So here you can see this is a freeze 5 setting, which corresponds to all layers frozen for products where the tensor contractions happen and readouts. So applying this to the OMAT and MPA, this would correspond to the freeze 6 setting, because we get another block around here, which is not trainable. So, yeah. Right, onto the benchmarks. So my colleague, Wojciech Stark, has designed some benchmarks. This is hydrogen scattering on copper surfaces. So again, he has trained a from-scratch potential, which was quite small and efficient. And we would like to have a freeze potential that will match the accuracy of scratch potential and use significantly less data. For the reference, Wojciech trained his model on more than 3,000 data points and spent, I think, about 500,000 CPU hours doing DFT. So here you can see the learning curves of the freeze potential. So sequentially from no frozen layers, so all layers active, this is freeze 0, and freeze 6, which in this case is everything frozen except the readouts. Here, the main message is that you can really deal with about 10 to 20% data and get the same accuracy as the from scratch potential. And does this apply to MPA and OMAT? Actually, no. So there we have a completely different trend. So for OMAT and MPA, which we think have significantly better lower level features and they have significantly better representations overall, we see that you really are interested in freezing no less than up to products. So if you keep more parameters active, you will see that your models will actually diverge. So your models will actually diverge, and you will get a less accurate potential. So Wojciech also produced some minimum energy paths. Here you can see the MACE MP actually doesn't perform that bad. It's qualitatively performs well, and we just fine-tune it to bring it to a good agreements with DFT and with our from-scratch potential. So the F4 10% and 20%, 10% and 20% are just the fractions of the training sets, of the original training set. Here we also have some sticking probabilities. Again, good agreements with, so this is an experimental curve, this is not DFT, and this has been rescaled to match the highest collision energy. Right, so now we have this accurate potential trained with just 10% of original data. So we saved about 90% of DFT formally. So that's good, but we're not going to have very efficient MD because even though some channels, it won't still be as efficient as ACE, for example. So we decided to use our freeze potential as a first principle method, just run some trajectories, do some k-mean sampling, and untrain an ACE surrogate on this generated data. And surprisingly, we found that we get an ACE model with matching accuracies to the freeze potential, but which is significantly faster on MD. So this is the second benchmark, courtesy of Connor Allen. So Connor was interested in constructing a phase diagram of titanium, aluminium, vanadium, and he has generated over 8,000 data points, which cost him about 1 million CPU hours. And he also fits an ACE, a custom ACE model, which is going to be our reference here. So this is not a MACE reference. So what was challenging about this data set is there is a liquid phase, and structures are not equally represented. So Connor designed a few benchmarks, which we, for convenience, grouped into 4 categories. So just training, validation, elastic, and vibrational. And the main message here that we'd like to convince you about is if you look at the area of those polygons, you can see that the freeze model on 10% data has roughly the same area as the ACE model, which we can conclude that they are essentially of a similar performance. So once again, a 10% data model wins here. And yeah, just apologies again for not presenting you the OMAT and MPA. I was really looking forward to that. But so just to summarize, frozen transfer learning allows you to achieve high accuracy predictions when trained on a little amount of data. Again, we are not concerned with transferability. So if you, for example, have a task where you had hydrogen and copper data, and you would like to have a potential that would potentially transfer to, I don't know, gold and hydrogen, you would probably need to use the multi-heads. This is not what freeze was for. And we have shown that a small, equally accurate potential can be trained with the freeze potential being the ground truth method. And yeah. The MACE freeze patch is available at the following link. Thank you very much for your attention.
Thank you very much. And we have time for one short question, and later we can also continue during the breaks. So if anyone has a question, feel free. Yeah.
Thank you very much for this nice overview. Is this, let's say, 90% less data needed universal per se, or?
As a conservative estimate, 10 to 20, but also we have seen cases where you need just 5%. So I would not make a promise that you would just need 5%, but I would say 20. You're definitely good with 20.
Okay, thank you so much. So once again, thank you, Maria. Andrea will present his work on scalable machine learning approach to light-induced order disorder phase transition with ab initio accuracy.
Okay, thank you. To talk to you about this, let's hope that it stays. Okay, that we recently published on MPizational materials. Sometimes. Okay. Okay, so basically I did this work in the University of Trento under the supervision of Professor Matteo Calandra and with researcher Giovanni Marini. So today I will talk to you about what we did, that is studying a very particular phenomenon that happens in silicon and that is non-thermal melting. And I will tell to you what is non-thermal melting, how we use the machine learning to describe it, and like the analysis that we did after machine learning fitting. So first of all, we see what is non-thermal melting in silicon. It's a process that happens in silicon and in other semiconductors. So we can imagine that a semiconductor has a valence band that is full of electrons. Then we have an electronic band gap and a conduction band that is empty under normal conditions. If then I take a femtosecond long laser pulse and I shine against silicon, if the laser is of optical wavelength, so basically the photons have an energy of 2 electron volt, 3 electron volt, bigger than the band gap, the photons couple to the electrons in the valence band and promote some of the electrons to the conduction band. So basically, some femtosecond after the laser pulse has arrived, I have a situation like this. Some electrons are in the conduction band and some holes are left in the valence band. What happens then is that electron-electron interactions formalize electrons in the conduction band to a Fermi-Dirac distribution with a Fermi level. And at the same time, hole-hole interaction in the valence band formalize holes to a second Fermi-Dirac distribution with a second Fermi level. And this happens on an ultra-fast timescale because within a given band, electron-electron and hole-hole interactions are very fast. What happens then is that on a much longer time scale, electron and holes recombine, so electrons will decay back to the valence band and we would go back to the original situation. But this does not happen on a femtosecond time scale. This happens on a picosecond time scale. So we have a scale separation in which electrons are constrained to stay in the conduction band and holes in the valence band. And they can be described by 2 Fermi-Dirac distributions. And this approach is called the constrained density functional theory and has been implemented by my supervisors in this work in Quantum Espresso. So we can do calculation of photoexcited materials with this 2 Fermi level approach and study how photoexcitation. And this is what we were studying in silicon. Okay, so now we come to explaining what non-formal melting is. So basically, in silicon, electronic states on top of the valence band are bonding states. So electrons are localized around the covalent bonds between silicon atoms, while states on the bottom of the conduction band are anti-bonding states. So basically, when I promote the electrons with the laser, I'm also depleting covalent bonds and weakening covalent bonds. So if the laser intensity is high enough, really the strike system gets disordered because ions are not left bound between each other by the electronic covalent bond. And the most interesting thing about non-formal melting is that this happens on an ultra-fast time scale of 0.1 to 1 picosecond, because as I told you before, this type of disordering of the system is related to electrons going to the conduction band and not to ions reaching the melting temperature in the usual way. But if I put it on this USB, can I put it on the USB key and go here, or it takes too much time? Because I really don't know. Or maybe I can try to use it like this. Ok, così. Sì. Ok, so Okay, it doesn't work. I try to say maybe like this. Okay, I'm very sorry for this inconvenience. Anyway, so let's come back to, I try to describe what non-thermal melting is. The situation is that people have done experiments about non-thermal melting, so people managed to measure the time evolution of silicon after photoexcitation by femtosecond laser pulse. This is one experiment in which people measure the time evolution of the density of states of the electrons after photoexcitation. And silicon is a semiconductor in the crystal phase, but is a semi-metallic and metallic in the disordered liquid and amorphous phase. So basically, if I measure that the band gap closes, this is a very strong signature of non-thermal melting because it's related to disordering of the system. And these people managed to measure a closing of the band gap a few picoseconds after photoexcitation. So this means that silicon actually underwent non-thermal melting during the experiment. And another important thing is that when the band gap closes, also the electrons that were in the conduction band recombine fast, because what prevented electron-hole recombination was the presence of a band gap, and now the band gap doesn't exist anymore, so electrons and holes recombine very quickly. Non-thermal melting can also be simulated in theoretical simulations like machine learning, molecular dynamics, or other type of molecular dynamics simulation. The recipe to understand that it is really non-thermal melting and not other types of melting is that we must compute the root mean square displacement, so basically the average displacement of atoms from the ideal lattice sites, and this must overcome the so-called Lindemann criterion. That is a very simple empirical criterion to describe that a system has become disordered, and this is usually set to when the average displacement of atoms is 15% of the nearest neighbor distance. Also, the root mean square displacement can be related to the Debye-Waller factor that can be measured by experiments, so it gives us a way to compare theoretical simulation and experiments. And last, we must check that the ionic temperature from the kinetic energy is below the melting temperature, because otherwise it would not be a non-thermal melting process. And actually, before we use machine learning to describe this type of molecular dynamics effects, people had tried to do the same with ab initio method. Like this is one reference from TD-DFT, so time-dependent DFT, in which the electrons are explicitly included in the calculations, the electronic occupations are explicitly included in the calculations, and so on. And in this reference, you can see all the features that I was describing. That is, the temperature is below the melting point, the root mean square displacement reaches the Lindemann criterion after 100 femtosecond, and they have managed to non-thermal melting in an efficient way, but these methods comes with some problems because TD-DFT is an ab initio approach, so it is very expensive computationally and limited the authors of that work to small systems, small timescales. And moreover, in literature, even beyond the TD-DFT, there was a discussion about the origin of non-thermal melting. Some people attributed it to phonons becoming imaginary. Other people say there was no phonon softening. So people were discussing about the true origin of non-thermal melting, and TD-DFT didn't allow to go to big system sizes to study effectively what was going on. And here comes our work. So we tried to use machine learning potential to describe non-thermal melting. So basically to describe the time evolution of the Debye-Waller factor and other quantities that people measured experimentally. And we try to use machine learning to use bigger simulation cells for longer times and describe better what experiments observed. So basically we fitted a machine learning model on two configurations. The first one are photoexcited configurations of a crystal with two Fermi levels that were computed in a constrained DFT approach because during the experiments, when we are in the crystal phase, we have two Fermi Dirac populations. After the system is disordered, the electrons recombine, as I told before. So basically, we included in the training set also amorphous and liquid configurations computed the old way with one Fermi level and one single electronic temperature. So basically, the novelty of this method is that we try to merge these two things together, so a photoexcited phase with non-photoexcited phase. We fitted a machine learning potential, hoping that it could interpolate well between these two phases and describe well the dynamics of non-thermal melting. As an architecture, we used the Gaussian approximation potentials because we started this work before all the fancy new methods came out. And now we will go very quickly to the results. So first of all, try to replicate the results from TDDFT that are given by the green line in this work. Our results are the blue line, and red dots are experimental data. So basically, we simulated a system with an initial temperature of 300 Kelvin. And so we initialized the system at that temperature, and we started the simulation with the photoexcited machine learning potential. And we find the same qualitative results that TDDFT and experiments find. For example, the Lindemann criterion is reached 100 femtosecond after the start of the simulation. And also the equilibrium value of the final temperature and final Debye-Waller factor are kind of comparable to experiment. But here we managed to run a simulation with 512 atoms in 1 day, while the TDDFT simulation were done on 64 and 216 atoms, and they would probably take many days or many weeks of calculation. So this approach is notably faster. And since the approach is faster, we managed to play with the starting parameters. So we tried to decrease the initial temperature from 300 Kelvin to 10 Kelvin, 1 Kelvin, 0.1 Kelvin, and we repeated the simulations. What we see is that when we decrease the temperature, the time scale for non-thermal melting increased to 500, 600 femtosecond, but it is still there. So we can even disorder a material with non-thermal melting even if the initial temperature is very, very low. And I think this is very interesting. The other interesting thing is that these three lines, they look very similar to each other, module a shift in time. And this thing really triggered us and led us to giving an interpretation of non-thermal melting that is given by the following scheme. So we must imagine that before photoexcitation, crystalline silicon is a system at equilibrium. So if we imagine to take one phonon mode as a representative effective particle for the system, it's at equilibrium. So it's moving in a potential that is approximately locally quadratic. Then we must imagine that photoexcitation arrives and suddenly changes the potential energy. The subject is suddenly changed to a quartic potential in which the particle is not anymore at equilibrium, but it's in a local unstable point. And it will start to fall towards the new equilibrium induced by photoexcitation with an initial velocity given by the temperature of the system before photoexcitation, and sliding down the quartic potential until the bottom. And what we tried to do was to solve the equation of motion for one particle in the quark box, and this is actually what happened. So basically, we managed to estimate very well the time it takes for the system to get to the first maximum in RMSD and in temperature, that is the red points down there. We managed to estimate them very well with this one-dimensional model. And in our opinion, this means that a phonon mode going imaginary is really what drives the non-thermal melting phase transition. As a last thing, we also said, okay, we know that in a supercell containing 500 atoms, there is 500 times 3 phonon modes. So we computed for the ideal crystal lattice of silicon with photoexcitation, we computed the phonon dispersion. So we computed all the phonon eigenvectors, and we computed the scalar product between the molecular dynamics trajectory and each of the 1,500 phonon modes. And we checked which of the modes were actually driving the molecular dynamics trajectory. And this is luckily the last slide. What we found is that basically the orange line is the contribution by imaginary phonon modes to the total molecular dynamics displacement. And we found that actually doing this scalar product, the most of the molecular dynamics trajectory is driven by phonon modes going imaginary, even if they are only 36 imaginary modes out of 1,536. So this is like the main result of our work, that we kind of confirmed that imaginary phonons play an important role in non-thermal melting when the system temperature is low, and thermal effects can be excluded. And as a very last thing, I want to thank my collaborators. This is my group at the University of Trento in Italy, the two people that authored the work with me, and that is a QR code to the publication if you want to have a look.
Thank you very much for working through the excitation. So any questions? Yes.
Thank you. I'm not sure I understood the TDDFT you use for simulate the to have a guess on the photodynamics. Do you have information about the forces and so, or this is just parameterized with your model in a sense?
Okay, so we did not do TDDFT. This was
okay.
But basically what TDDFT does is a sort of ab initio molecular dynamics scheme in which the electrons are not given one Fermi Dirac distribution at every time step, but the electronic occupations are varied in time. So basically they started with a system at equilibrium, then they coupled the laser to the electrons, so they evolved the occupation of each electronic state independently according to detailed balance and according to the laser pulse that is coming. And basically for each time step, they study the time evolution of the occupations of the electrons, and they do a DFT calculation of forces on the ions, taking into account the occupations that they just evolved. So basically it's an iterative scheme in which I update the ionic positions, I update electronic levels and occupations, and I use them to recompute new forces on the atoms and so on. While what we did was classic molecular dynamics with a machine learning that effectively learned the effect of photoexcited electrons.
Okay, maybe I will ask you after.
Yeah.
Thank you.
Okay, one more question.
Hi. So what I don't understand is in your molecular dynamics simulation, what happens to electrons? So these photoexcited electrons in holes. So do you fix always in each step the number of electron holes, or do you fix the Fermi level?
Okay, so we fix the number of photoexcited electrons in computing the data set. So basically, when computing the data set, we said we take a bunch of crystalline configuration, and in all of them we impose the same amount of excited electrons and the same electronic temperature. Because what happens in experiment is that the electron and hole population remain separated until the gap closes. And the gap closes when the system is disordering. And when the gap closes, electrons and holes recombine on a fast time scale. So basically, one of the approximation of our work is that when the gap closes, we discontinuously switch from a 2 Fermi level description to a 1 Fermi level description. And before that, the amount of excited electrons is constant, and after that, the electronic temperature is constant, and we have only 1 Fermi level. This is a thing that we are working on improving, like including, for example, electron coupling to introduce a time evolution of the photoexcited population and of the electronic temperature, but we are still working on that because it's not simple. You need to take into account many effects and so on.
Okay, thank you.
Okay, thank you. We'll have from EPFL with his talk on exploring chemical space for singlet fission materials with generative design.
Right, thank you so much for your introduction. And I'm Thanapat, a PhD student at PFL, a part of Professor Clermont's assembly group. Today I will be talking about my work on using generative model for exploring the chemical space for these target molecules of organic electronic materials, particularly for singlet fission application. So with the amount of data we have available this day in PubChem 60 and recently OMO 25, leveraging them to drive molecular discovery has been successful in many applications. But there are many ways to make use of these data. The most straightforward approach is just simply to screen this large chemical structure database to find your target molecules with high throughput virtual screening, while being the most straightforward here. You also have this to be the least efficient way to do it, and you also have the exploration process to be pretty much limited to these predefined molecules in this database. So in terms of the search space here is also the smallest. And then you have this fragment-based approach that kind of partially solves the issue in terms of research space by creating new molecules based on some predefined fragments and some rules for how to put these fragments together. And then couple this with some optimization algorithm like genetic optimization or particle swarm optimization. You are then able to efficiently explore in this combinatorial space for your target molecules. So previously, my group has developed some tools to support these data-driven molecular design. We have this tool called Cell2Mo that enables us to mine and curate data CSD, and we have already used it to build a number of molecular structure database, Form for synthesizable molecules, OSCAR for organocatalysts, and recently TVM-QM for short metal complex. We also have this another tool called Navigat-GA, and as its name may imply, enable us to do molecular inverse design based on genetic optimization. So we have already applied these two tools for a number of molecular design applications already, but the one that I will be focusing on here is to find molecules with single efficient properties. It's a phenomenon of splitting this this S1 singlet exciton to two T1 triplet excitons, and this can be leveraged to improve power conversion efficiency of this semiconductor by double the number of current generated from one photon absorbed. For a compound to be considered as viable single efficient chromophores, it has to satisfy a number of energetic excited state criteria. So first of all, for the split to be feasible, you need to have the S1 energy level to be roughly twice larger than over T1, and the S1 as well should be within the visible light region, and the T1 should also be compatible with this semiconductor band gap. So previously, we leveraged our own database containing 100,000 molecules mined from CSD using our Cell2Mo tool. We also perform TD-DFT calculations to annotate all of these molecules for their electronic Ts, and then we derive molecular building blocks based on chemical structures in our Form database, and that enable us to perform high-throughput virtual screening on these recombined molecules, as well as genetic optimization to identify some single efficient chromophores. So following this fragment-based approach for molecular discovery, we previously predominantly identify these three classes of single efficient molecules. So this BodyPi, Acin, and Mesoionic. By the time of these publications, you could indeed consider these structures to be new, but they all kind of fall within known established family of single efficient molecules, which is kind of to be expected of fragment-based approach for molecular design because it's inherently constrained the discovery process, the molecular generation process, to known predefined scaffolds of molecules. And this led us to this more novel approach for data-driven molecular design by leveraging this type of deep learning model, the generative model, that can streamline the process of molecular generation. Instead of relying on some predefined rules and fragments, it can simply learn to generate new molecules from some chemical structure database, and thereby being able to potentially explore in broader chemical space and find more types, more families of target molecules. In my implementation here, I implemented this well-established generative deep learning platform called VNVent, which itself is recurrent neural network designed to learn smart string as molecular representation. I also integrated ChemProp, which is a graph neural network, to evaluate excited state properties of generated molecules during this process. And I coupled these two models together to reinforcement learning curriculum, which optimized the generative process from just generating random molecules to generate specifically single efficient target molecules. And I perform reinforcement learning here in stages, having the first stage to focus on the structural aspects to avoid some unwanted, undesirable moieties, and also to encourage the model to generate neutral molecules. The second stage is where I delve into relevant excited state piece to single efficient. So considering here the single efficient energy score, which is our divide metrics to indicate how we align S1 T1 energy level of the molecules are to the single efficient requirements earlier. We also consider the exciton size because larger exciton size can encourage the splitting. And lastly, the T2-T1 gap to avoid the upward conversion process. So all these three objectives are supposed to be maximized. So first of all, let's take a look at our reinforcement learning optimization of our generated molecules. And we can see improvement overall excited state properties that consider here, being able to generate molecules with larger exciton size, larger T2-T1 gap, and most importantly, better S1-T1 alignment with zinc efficient criteria. Comparing the molecules generated at the beginning, we have these random molecules having the S1-T1 distributions to be kind of overlapping, which indicate that most of these generated molecules do not satisfy our zinc efficient energetic criteria. And after our reinforcement learning optimization, on the other hand, we have the model that is capable of selectively generate molecules to be zinc efficient, having the S1-T1 energy distribution to be clearly separated, and having the S1 distribution to be roughly twice that of the T1, which is exactly what we are targeting. So in terms of the properties, it is fairly successful, but looking at the structures generated from this optimized model, and they are predominantly these polyene acene-like sort of structures having this extended conjugated system. These structures are indeed good as zinc efficient, but they are simple, structurally speaking, and therefore can be considered as like the first local minima in the real space for reinforcement learning to discover. But here I want my generative model to be able to explore in broader region of the chemical space to find more types of molecules for zinc efficient. And to do so, I introduced this penalization term to punish the model for ever generating the already discovered families of molecules. And then I just simply perform the optimization multiple times. At the end of each trial, I just simply add the already discovered families of molecules to the unwanted list. And here I have 10 optimized agents, 10 optimized generative model that can selectively generate the zinc efficient chromophores, and they also correspond to different regions of the chemical space as well. And thanks to this ability to be able to explore the chemical space broadly, I was able to come up with diverse families of zinc efficient molecules. So initially, I just discovered the same molecules as the fragment-based approach, these polypi, acene, and mesoionic. But then my generative model was able to come up with more diverse types of zinc-efficient chromophores, these benzopyran, silene, flavonoid, quinoidal, and carotenoid. And among these new molecules we were particularly intrigued by this new molecule we discovered, and we call it neocoumarine because it shares stark similarity, structurally speaking, with this non-compound coumarine and isocoumarine. And they themselves are really well represented in our form database as well, used to train all the models, but they do not have suitable S1-T1 energy levels for zinc efficient application. But the RL was able to leverage this well-represented type of molecules in our database, make some slight amendment, and then come up with this novel type of zinc-efficient chromophore, which actually turns out to be synthesizable as well, as established by these papers in 1970s. We also with some local chemical space exploration and come up with some more derivatives of this new neocoumarine, or exhibiting desirable energy levels for zinc efficient. I also modified these structures manually as well to extract the underlying design rules. So firstly, I just tried to vary the number of fuse rings, and that turns out to be a bad idea to seem to be the most optimal. But by changing the functional group from ester to be something else, or by changing inside fuse ring, this seemed to enable this zinc efficient to remain, unless you alter the ring aromaticity. This also hurt the zinc efficient. And this allows us to add this neochromatin with this well-established family of the sync-efficient chromophore called benzofuran. So both of these two, they have autokinoid structures, being this aromatic ring, having this auto-exocyclic double bond, and then being capped by some sort of functional group. In our case, that would be ester. In the case of benzofuran, that would be just ether. So both of these two can be synthesized. They also have good S1T1 and T levels for syncate fission. We also computed for the diradical character, and these two turns out to have good diradical characters for the syncate fission. But in terms of the T1 energy, we have a slight advantage here. Our new chromatin has T1 of around 1 point, which is more compatible with the semiconductor band gap in comparison to the benzofuran, whose T1 is typically too low. So to conclude here, I have established a fully approach for molecular design by incorporating generative model with property prediction model to reinforcement learning. And with this pipeline, we were able to explore the chemical space broadly, be able to come up with diverse range of our target molecules for syncate fission application. And among these new molecules we identify this new and also the synthesizable scaffold for syncate fission based on this neochromatin, or more formally 2-benzopyrantrione. Thank you so much for your attention.
Thank you very much. We have time for one short question, if someone wants to ask.
Thank you. In perspective, do you think could explore also this, not only the chemical space, but so many of this system will be thin layer or so the packing itself, the relation between the molecule will influence the actions and all the properties. So, do you think it's doable somehow? Thank you.
But I think it would be difficult to take into consideration directly within reinforcement learning loop, because you need to compute these properties, right? You could use it to build candidate molecules later, potentially.
Okay, thank you once more. Next, it's a great pleasure to welcome Professor Tristan Barrow from Heidelberg University. He will present first intro lecture on coarse-grained models, and after that we will have a coffee break and then tutorial. So, please.
comes out so poorly. But I think we'll get this. Yeah, I think I'll do. Yeah, all right. I'm sorry. I apologize for the resolution. Yeah, thanks very much. It's my pleasure to. It's a great pleasure to be here. I'd like to thank Katarina, Federico, Juraj, Ivor, and I'm really enjoying the summer school. I will change gears. I'm going to talk also about molecular discovery, but I'm going to talk about a very different class of systems. I want to emphasize and fun soft materials. So think complex liquids, biomolecules. I'll show you mostly applications in biomolecules. And so I'll give a bit of a background to sort of give you some of the constraints and the very different physics that we work with. And so that leads to very different types of methodological decisions that we have to make in order to get to, you know, a high throughput regime and then you know, to do molecular design. And so what I'm going to get to is the use of coarse-grained models to work with these types of systems, and in order to explore the underlying chemical space. I'll talk about, I'll introduce these coarse-grained models. I'll talk especially about what transferable coarse-grained models mean, and then show some applications. All right, and so before I do this, let me thank the people who did the work. I'll talk about work from Argo Dut, Karen Kanekal, Roberto Menichetti, Bernadette Moore, and Louis Walter, who is here, and he will actually give the tutorial in the very next session. And so before, to motivate things, I thought I'd start with on a tangent, and so I want to talk about Levinthal's paradox, and so maybe not all of you know about Levinthal's paradox. And so this was formulated by Levinthal in the 1960s, who's a biochemist, and this is at a time where protein folding was sort of starting up as a field. So in the 1960s, we started having the first few experiments on proteins, looking at protein structure, and there are famous experiments. For instance, you go back to the work of Van Vinsen that showed that they could measure the structure of a protein in its folded state, and then they could denature with a co-solvent like urea. Let's see it unfold, and then if they sort of wash out their buffer, it would refold. And so this would show that, you know, with a very simple system, simple PEP, there was no need for sort of complex biology to observe or have protein folding. And so there's something sort of very robust behind this that's not completely clear. And so Levinthal formulated this what comes out as a paradox, and saying that, you know, if you think about, so protein is a long polymer with many different, so each unit is so there's different types of amino acids. And so if you consider the number of microstates of this protein can take, then you will have, you know, a number m of microstates per amino acid, and then be n amino acids, so these n units in your polymer. And so, you know, simple scaling would tell you that then the number of microstates you would expect would grow like m to the n, right? So there would be some scaling. And so then Levinthal says, well, if the protein was to spend 1 femtosecond in each one of these microstates, it would take longer than the age of the universe for the protein to fold. And so that doesn't work. And so behind this, the implicit assumption is that the energy landscape looks like this, right? So it looks like a golf course where all the protein configurations are flat for the native state, which would have a lower energy, right? And so it's clear that it's not the case. You have different configurations. There's going to be, you know, interactions due to atoms at different places, and so this will sort of shape the energy, and this will create an energy landscape that does not look like an energy golf course. And then you apply the Boltzmann distribution. It's very clear that this does not look like this. In fact, you know, many experts, you know, simple peptides that fold quickly have an energy landscape that looks a bit more like that. If you think that this is sort of a curiosity, all scientific history, think again, because Levinthal's paradox is mentioned on the first page of the scientific background of the Nobel Prize in Chemistry from this year. Well, they discuss Rosetta fold and AlphaFold. So the reason why I talk about this is twofold. One is that, you know, I want to bring attention to the fact that, you know, I don't think materials discovery, just like this system here, this problem here is serendipitous. You know, there's a landscape underneath it, and so you're really sort of falling down the landscape. And the same thing happens in materials discovery. And so a lot of the methods that, you know, have been discussed so far exploit the fact that, you know, materials don't live on a golf course. And the second aspect is I actually want to stress the conceptual links that happen between exploring these microstates, so exploring conformational space, if you think about Boltzmann distribution of a statistical mechanical system, and exploring the material space or the chemical space when you're doing some sort of molecular materials optimization. And I'll come back to this concept. Okay, and so what it would look like if you're doing some sort of material discovery is maybe, a modern approach would look something like this, where you have maybe a high throughput cell assay. This is probably maybe a picture at least I have in my mind of how drug discovery might work in a pharma, and where you have many test tubes, and then you're trying different molecules in each test tube, and then all of these molecules are exposed to the same environment, same protein, in the same buffer, and then you're going to make measurements for all of these. And then there's different things I'm going to talk about that have been mentioned in this summer school already, but so I'll try to sort of briefly recap them in the spirit of, or in the context of soft materials. One is that we're going to think about a space over which we want to, and so I'm going to call this a chemical compound space. We will not be working with electronic properties, which have been discussed mostly so far, but we'll work with thermodynamic properties, work with liquids. And then talk, of course, like many others, in terms of what can we do in terms of optimization, and then both in terms of finding new material discovery, but also we're interested in maybe learning something about these systems, and so that maybe we can get a little bit of insight. And so the comment, so something that typically, then the idea is that chemical space is large, or any sort of material space you're considering would be large. Large with respect to, so this chemical space would mean here all the small molecules I'm going to consider here. Here I'm going to be interested in small drug-like organic molecules. And so that space of all the possible molecules I could potentially choose out of is large. So large with respect to what? Well, one thing is that you can look at it with respect to the types of data of compounds for which we have experimental information, right? And so compared to the number of compounds that have been synthesized, it is a particularly large space. Also large is that in the sense that we don't have enough material in the universe to synthesize all of them, and so you will have to make choices, and you will not be able to synthesize all of these compounds. And maybe that's okay, because maybe not all of these molecules to be interesting. And so, just like in any other, for any other scientific application, then what we work with is a typical inverse, in that we have a number of compounds, that we're going to choose from, and then the only thing we can do is a forward measurement. So running an experiment or a simulation or a quantum chemistry calculation would consist of doing a forward measurement that links from chemistry to a particular value for your material properties. But then what you're really interested in is this blue arrow, and sort of like saying like, I want a particular property. What type of chemistry do I want, right? And so we've heard this in the last talk, for instance. And so that's a typical inverse problem, and so that motivates the use for data sets that then allow us to do all sorts of statistical inference, and in particular, there's been a lot of machine learning going on in terms of building models that allow us to solve this problem in one way or another. And so, of course, the typical issue that we suffer from, that many of you do suffer from as well, is that we work in a low data regime, so we have few data points that are available to us, and so we cannot just like throw more data at the problem. Data points are expensive; they're difficult to get, and so there's a different there's strategies that have been proposed by the community in trying to mitigating these issues. And one thing I'm going to emphasize here, especially 3 and 4 in particular, sort of the fact that we can screen efficiently our chemical space by multi-scale modeling, in particular coarse-grained modeling. We'll sort of link back to this concept of experimental design, which will give us to some sort of machine learning guided design, which will also, spoiler alert, will be this topic of the that will be given by Luis next. Okay, and so soft matter is a whole bunch of systems that you've for sure interacted with. You're made of it. It's all sorts of materials. So things like liquid crystals, amphiphilic molecules, soap bubbles, polymers, proteins, colloids. And the characteristic property they work is that the characteristic energy is small, so it's on the order of kT, so kT is thermal energy, and so it means that thermal energy is strong enough to shelter the structure of these systems. And so this allows the system to display sort of very unique things such as spontaneous and then large mesoscale structures. For instance, a soap bubble is an example of a large mesoscale structure and that spontaneously self-assemble, right? And so about then the types of energies that are going to be relevant, and what it tells you is that the interactions that are relevant are going to be mostly electrostatics, and it's mostly going to be a mix of fixed and fluctuating electrostatic Coulomb interactions and van der Waals interactions, basically. And then in soft matter, like even worse than in hard condensed matter, we suffer from poor scale separation. That's hard for us to separate between in terms of our systems in terms of length and time scales. That makes any sort of theory or modeling approach particularly difficult because you have this inter scales that happens all the time. And the another aspect is because these systems are they're called soft for a reason. There's going to be many different types of configurations that are going to be relevant, and so we cannot really start from one configuration and then do some sort of a harmonic approximation to approximate the types, the ensemble of configurations. So we really have to do a lot of work in the configurational sampling, and this will limit the type of methods that we work with. And so concretely, we're not going to be able to work with quantum chemistry methods. They're too expensive. We have to work with classical simulation methods like molecular dynamics. And the idea here is that, if you want to compute stability, then the relevant metric is not the energy, but it's really a free energy because you have to take into account entropic configuration. So, this is a standard plot. You've all seen this. This is to motivate that, systems display different length and time scales, and we have different theories that sort of try to tackle these systems at length and time scales. And so here we're really working with classical models, so particle-based classical models, and so we're solving Newton's equations of motion, and in particular, we work with these so-called coarse-grained molecular dynamics models, and I'll show you in a bit more detail, but it's sort of, if you're used to working with quantum chemistry, it's not just that we get rid of the electron, we also get rid of atoms, and so you're probably going to, you're probably frightened at the moment, so my job is to try to convince you that there's still something to be rescued, and there's something that's interesting behind doing this. Okay, so we coarse grain, so it's not completely arbitrary. So there's a lot of simplification going on. If you think about modeling, there's always some sort of simplification going on. It is actually in quite a bit of physics. Think about renormalization group theory, but also in particular in polymer physics, blob picture scaling concepts, etc. It's really sort of applying these ideas to molecular systems, right? And there's sort of number of heroes in the field that have been doing this for the last 30 to 50 years. And one of the first sort of really motivating study or paper that really went into this direction is this paper here that took a polymer, so that's a polymer, and then described it not atomistically, but with this very simple bead spring toy model here. But then they did try to reproduce the Boltzmann distribution of the original. There's a marginalization of the original Boltzmann distribution here, and this they did then connect this viscosity parameter between their simulations and the experiment. This was really sort of a indicative and sort of one of the pioneering papers that really showed how trying to go into predictive modeling for these types of soft matter systems. And so in many cases, what we're doing is, going back to this fringy landscape that we have, we're talking about self-assembly. So we want to look and observe our system in its native state or its most likely state. So really what we want to do is to run simulations in order to surround this conformational landscape and then observe self-assembly. And so coarse graining, sort of really roughly speaking, would consist of sort of shrinking the size of this this fringy land, of course, then the self-assembly process will happen more easily and faster. And so, if nothing else, then coarse-grained simulations hold the promise of faster simulations, right? Which is not the only reason why. And so if you think about then doing materials discovery with these systems, then that poses a bit of a challenge because, first of all, if I want to work with to simulate and study one system, then I have to solve this self-assembly problem, meaning I have to explore the fringy landscape sufficiently such that I can get a good view on this probability distribution or the fringy landscape. But if I'm interested in doing materials discovery with these soft materials, then I have to solve that self-assembly process for every single one of these points, right? And so that shows you that there's really two landscapes that are relevant. One is a conformational landscape, and the other one is a compositional landscape. And the problem compounds in that I have to solve both of them. And so this makes soft materials discovery, challenging. So coarse graining takes many different forms. This is how we do it. So this is how we do it in the group. So we work a so-called Martini model. And so instead of describing a molecule with all its atoms, we describe it in terms of, roughly speaking, sort of like these beads that look like functional groups. They're not exactly functional. You get the idea. So a couple heavy atoms. And so we're going to, integrate Newton's equations of motion at this resolution, right? So we don't have information about all the atoms. So that's what I mean by coarse. And there's two main different ways of parameterizing these models. And it's very intuitive in that if I have a model that lives here on this multi-scale plot, if I want to parameterize this model, it has to be informed, and it's informed either from information that's below, so quantum mechanics or atomistic molecular simulations, or from above, and this sort of large-scale physics, phenomenological physics, or sort of, some experiments. And so we'll use this top-down approach, which is more phenomenological, and this leads to a whole class of model. It's typically called transferable. They're transferable that they are defined in terms of interactions as a discrete set. And so this is really like, so each color here is a different type of physical-chemical interaction. And so this is like having different Lego bricks, right? And if you want to build some object, you only have a discrete set of Lego shapes and colors in order to build. And so you're limited in terms of the original building blocks in order to build something. And this has advantages because it allows us to sort of click together models, and it makes these models sort of extend to other molecules, and that makes them transferable. So that's sort of a curiosity, but it has a large impact for us. So one sort of early, example of a model like this that you may have seen is this HP model, that's for hydrophobic and polar. It's an early model again for protein fold. You can see I like protein folding, and so HP meant that the proteins were modeled on as a heteropolymer on a lattice with only, you can see, like reads, and so these were either hydrophobic or polar. And because you only have two B types, then as you can imagine, there's a lot of sequences that you're mapping to the same, HP resolution. Because you cannot tell apart 20 amino acids onto two. And so you sort of have an information bottleneck that happens at the sequence space. And so the sequence space of model is a lot smaller than the sequence space of proteins. And the same thing happens for a model that we're using, in that there's a lot of molecules structurally and mostly thermodynamically similar that end up in the same representation, because we just don't have enough, Lego building blocks to tell them apart. And that you will say this is a bad thing because we're losing resolution, right? We cannot tell apart between these different molecules. That's true. On the other hand, the great thing is that I only need to run simulations for this particular representation in order to make an estimation for this neighborhood of chemical space. And so this is going to be super, very efficient and useful in chemical space. And this is an aspect that maybe not so intuitively is not something that depends on the structural mapping. So how atom mapped into beads, it has nothing to do with it. It only has to do with how many bead types, or how many physical-chemical interactions I'm distinguishing. And what it means is that I can tune how many of these interaction types I'm introducing. And by tuning this, I can systematically tune the size of my chemical space. And there's an exponential relation between the types that you introduce and the size of chemical space that you get. And so what it means is that the fewer B types that I use, the smaller the chemical space, and so the easier and faster it's going to do materials discovery in that space, at the cost of resolution, of course. So this is how it looks like. We start here with this example. This is an example from lipid membrane permeation, so solute permeation in the membrane. We start with, I think, about 500,000 molecules. We coarse grain them all. So we coarse grain them to the coarse grain model, this Martini model. And so we're left with much fewer compounds to simulate, not 500,000, but much fewer, on the order of 1,000. And for each of these, we run computer simulation with the lipid membrane. We can then we compute free energies, which are going to be the stability, which are going to give us the stability estimate. And then from that, we're going to sort of point onto a low-dimensional representation. Right? So a couple of things about that. The fact that we coarse grain sort of reduces enormously the amount of compute that we need, because there's coarse graining happening before we run any simulation. And this is very different from, say, high throughput DFT, where you're going to have to run the DFT every single compound, and then in the end, you want to project it down to some, low dimensional interpretable descriptors or reaction coordinates, and so all the course at the end. So here, a lot of it happens before, which makes it very computationally efficient. Also, it tends to smoothen our chemical space, and so it typically helps suggesting actually one-dimensional representation. And so finding structure-property relationships ends up being a lot easier. One aspect, and this has been discussed a bit, talked of the tutorial of Jonathan this morning, that if you're going to do things at high throughput, then you have to be a bit serious about things such as reproducibility. And so this is also something that with these coarse grain simulations, and the framework is very similar. We also work with computational workflows that then allows connects direct Nomad, which is a large research data infrastructure for different types of quantum chemistry calculations, molecular simulations, but also experiments. And so the research data infrastructure in the sense that you can just upload the data and then the metadata is automatically extracted, so you don't have to do anything. Okay, so a couple so applications we do with this. We can do a bit of inverse molecular design, so find some relevant chemical groups. We've learned equations. This was done with compressed, and but then also looking for compounds that were altering the phase separation of lipid membranes. I'm not going to talk about these more. I want to talk about we'll talk about one particular application. Of a molecular optimization exercise or problem. And so one aspect, so I wanted to come back to this slide here, which shows you that as we reduce the number of interaction types, then we reduce systematically the size of chemical space. So here in this particular context, this is a very rough estimate, but there's probably about with this very simple and coarse force field, then we have a million or so coarse grain representations that try to estimate a very large neighborhood of the space of small organic drug-like molecules. That's still a bit large. We could do fringy calculations for 1 million molecules for the types of systems I've been showing you. And so we do want to make this even more efficient. And so there's two things. One is that we need to efficiently navigate it. And so we'll do this by learning a low-dimensional representation. And the other one is that we want to efficiently optimize. And so this has to do with then that we want to minimize the number of computer simulations that we run. So then this goes into active learning and things like this. And so this is my slide on I think if Milica talks about Bayesian optimization, she'll probably do a better job than I will. But since I'm scheduled before, so here it goes. So we want a cartoon representation of our chemical space, and on the vertical axis would be the target property of interest, right? So maybe it's a free energy that we're interested in minimizing. we want to do this by minimizing the number of computer simulations we have to run. And so it's an optimization strategy. It's sequential in that we're going to do it so basically we have a function that we're trying to minimize or maximize. And so the way this typically goes that you build a surrogate model for that objective function. So it's going to be a simple machine learning model, in this case, a Gaussian process regression model. And this will help us choose the next points to evaluate. So this is shown in this a little movie that I'll let run. So the reference for the function is in black, and then in purple is our current surrogate. You can see that it's exact where points, and then we're going to start adding and decorating it with more and more training points. And you can see that the function, the purple function, becomes more and closer to the true reference. There's two important aspects. One is that it's useful to have a continuous space in order to do optimization. And that's a problem for us because our chemical space is discrete, right? So we have to do something. And then the second is that we want to have error bars, and so something like a Gaussian process again will allow you to can get you error bars. So so this is our setup. We take our chemical space, our coarse-grained chemical space, and then we project it down onto a smooth, continuous latent space in order to do it and do optimization in that space. We then connect it to a surrogate model here to predict whatever target property we have, and then we're going to use Bayesian to guide us and tell us what should be the next computer simulations to run. And so the Bayesian has to do with mitochondrial membrane selectivity here, so mitochondrial membranes have particular lipid compositions that are lipin, and there's interest for aging of the cell and also for diseases to measure the content of cardiolipin you have in your mitochondrial membranes. And so there's very few models exist, and so that means you cannot just use experimental data. There's just no experimental data. And so this is why we had to do this in silico. And so we look at selectivity and that we wanted to bind to this, but not bind to other lipids. And as you can see here, this is basically this cardiolipin lipid, but cut into two. And so this is a bit of an entropic problem. And so we'll compute free energy differences between these two states. And so this active learning loop looks like this. So we're running our free energy calculations with coarse-grained molecular dynamics. We use this to retrain our surrogate model in our latent space, and then this will then be used to evaluate our acquisition function with the Bayesian optimization, and then it'll suggest new and then we'll feed back this into the free energy calculations, and then we do this a few iterations, and then we try to converge. In the end, we converge by sampling, I think, less than a half a the total space, so there's very few simulations we actually run. And what we get are design rules as to what should be the types of coarse grain that we should work with. These are, by the way, very interpretable because they're linked directly to hydrophobic interactions, charges, because of the nature of the coarse grain model. So that makes it very easy to Now, of course, experimentally, then our collaborators want to have a particular compound. They don't want to have a coarse grain representation. They don't really care for this, and so you'd want to sort of reintroduce information. And so one thing we've proposed back in a few years ago was to use generative models to reintroduce information. It's a very natural way of generating atomistic configurations conditional on the coarse grain degrees of freedom. It's been picked up by many groups since. That's not what we did here. Instead, we took a vendor and then we filtered it according to our design rules, and then we shortlisted about I think 20 compounds, and then we did find 3 that were active in vitro and 1 that was active in vivo. Super exciting because this is I think the first study that shows that you can use coarse grain simulations to then design a compound that is active in vivo. All right. You can sort of further accelerate this molecular optimization by working with, by exploiting this aspect of different types of position of our driving forces, leading to different sizes in chemical space. And we do this by, so this is Lewis's work, where he takes a low resolution coarse grained force field, a very smoothened chemical space where we can do Bayesian optimization very quickly. And then he can then reintroduce information, work with more detailed force fields that have more actions, more subtleties, and but lead to a chemical space that has a much more rugged landscape. And so we can connect these into a so-called multi-level Bayesian framework where really your surrogate function is informed by the previous level. And then you set sort of target accuracies to then change up levels. And he applied it to, again, solutes that alter membrane phase separation. And you can see here sort of a projections of the different chemical spaces from low to high resolution. And you can see how he goes very broad exploration to a very focused and narrow exploitation of the different points of different neighborhoods, chemical space neighborhoods of interest. And also he is indeed more efficient than doing single-level Bayesian optimization. And this is what you will do in the tutorial. All right. How much time do I have? 5 minutes? 5 minutes? Okay. I think I'll be done in 5 minutes. All right. So I just want to finish with talking a little bit about. So we're often interested in not just discovering compounds, but we want to understand what were the driving forces. So there's a certain amount of interpretation you get, and that's from the fact that we start from our graph representations here come from or are informed by a coarse grain model, which is sort of physics and chemistry based. All these parameters in terms of hydrophobicity and Coulomb interactions, and so that does lead to quite a bit of interpretability. However, I told you that we did this onto a low-dimensional, smooth latent space. We did this with a regularized autoencoder, and so this is a deep neural network, and so this is nonlinear, and so it's hard to sort of backtrack information and reverse the information and going from the latent space back in and explaining what types of features are important. And sort of limitation of the method here is that, as you can see, and I didn't explain too much, but the representation we use here only depends on the solute. So it only depends on the molecule itself, and it knows nothing about the environment. Clearly, if I insert a molecule, in a liquid, then what the liquid is will matter, right? Whether I insert this in water or oil or next to a protein will have an impact. And so what we tried is to change the representation where instead of just encoding the solute, we encoded sort of a neighborhood around the solute to get the solute with the environment. We used a representation that was richly designed for DFT calculation called SLATM, which is a number of 1, 2, and 3 body interactions. So it's shown here. I'm not going to go into detail, but basically, you'd have this the chemical elements, and then the 2-body term will basically represent some sort of radial distribution function, and then actions as an expansion over the many body configurations that you have around the solute. And what you can do with this is that with this representation, you can get away actually with doing principles, and there's naturally sort of a separation between the high selective compounds and low selective compounds. And so what it means, and this is not so surprising, is that if you have that encodes more physics, what the physics and the chemistry of your system, then you can get away with a simpler dimensionality reduction technique. And so consistent with many other studies. All right, let me finish. I'll skip this. And I'm coming to the end, so I wanted to sort of motivate again this perspective of working, sort of not for one particular molecule, but across chemical space. I think this is something that many people do in the summer school. Hasn't always been the tradition, and so that means that when we're setting up our force fields, running simulations, analyzing this, we're doing this across neighborhoods of compounds. So we have to be wary of this and sort of finding benchmarks that allow us to validate our methods against or across these neighborhoods. And a specific point that maybe trying to bring home here is the role of coarse graining and how it's it's trying to help impose some sort of scale separation discovery problem. And it's helping sort of finding structure property relationships by basically smoothing our chemical space. And this is something that really helps us in relationships and also doing compound discovery. And thank you so much for your attention.
Thank you very much. We have some time for questions, if someone wants to ask.
Thank you very much. It was very interesting. I guess the equivalent to, for instance, what I do now in coarse graining would be trying to find the interactions between, and I know that a lot of groups that do that, us included. But I've seen essentially the decision of the bid itself being relegated to chemical knowledge, essentially, especially where you are trying to build hierarchical models of different bit sizes, essentially. Do you envisage there is a way of some sort of collective variable can automations between the different level of accuracy in a coarse grain model?
If not, we proceed with coffee break. Thank you.
Maybe I'll just do a quick comment. So probably you've seen there are poster panels near the coffee, so you can put your posters and have them. Yeah.
I think it's not even. Okay. 1 second ago it switched, but I don't know. Maybe, I don't know. As you, what do you think? Increase. Yeah.
Okay. Hello, everyone. So I will do the tutorial for the lecture which we just heard, and we will do a molecular optimization with coarse graining. And yeah, so we'll do it as slightly differently than the other tutorials which we had, because I think it's not so easy to follow the notebook and at the same time listen to what I'm speaking. So the idea is I first shortly introduce the goal, and then you have some time, like 30 minutes, to go through the tutorial yourself. And I mean, there's also a lot of text explaining things, and then you can actually read this and check what the code is actually doing. And then we will discuss the results in the end. And the idea is, in general, to keep it as simple as possible, this molecular optimization. So we also don't use any fancy library, which you then don't understand what is doing under the hood. So the only helper code is in this script, which is in the same directory. So it's not super relevant for the tutorial, but if you're interested, you can have a look and then understand all the details. So yeah, and now to the tutorial task. So the idea is to find a molecule which, using the coarse-grained models, which has a preference for the for a hexane water mixture in comparison to being only in the pure, one of the two solvents, like in the pure version. And so in comparison to, that's what Tristan already mentioned, in comparison to other materials discovery projects, when we talk about small molecule discovery, the properties always depend on the environment. And in this case, our environment is super simple. It's just a hexane water mixture. But then, so the preference for being in one of the different solvents can be quite different. And yeah, so we characterize this preference for being in one of the solvents as a free energy. So that's another thing which Tristan already mentioned. It's not a single state energy which we are interested, but the free energy, because the entropy plays an important role. And yeah, now I introduced everything, and now you have like 30 minutes maybe to go through it. And if you have questions, just raise your hand and then I can help you. Every still except I think 2 simulations which we perform should execute super fast, and if they are slow, then it's probably a problem with the server. And then I don't know, maybe I have an idea how to make it faster, so you can also ask me. Okay, yeah. Can also, okay, I still continue talking. So there are like these 6 sections, and first one just introduces the coarse graining, but we had like a similar thing in the presentation already. And then the second point is we look at the hexane water system. We do a short simulation and see what it's doing. And then we consider coarse-grained molecules, and then do an encoding, because afterwards we perform a molecular optimization based on Bayesian optimization in this encoding space. Next, we will not go into the details of the Bayesian optimization here, because this will be covered, I think, tomorrow. Yeah, and then part 6 is, if you have more time, then actually like task where you have to do more coding, but we will discuss the results in the end. Okay, so I think since we only have 10 minutes left, I want to now discuss results. I hope you, maybe not got to the end, but got at least the first steps. I wanted to mention initially, so the first 3 points are not related to machine learning at all, but only like preliminaries. And then the fourth and the fifth point are machine learning related. I hope you at least got to the fourth point, but yeah, we will discuss the results now. Yeah, so this is just an example structure, the coarse graining type we do. And then the interesting thing is we run the simulation of our hexane water mixture. Should be rather fast. I think some people had problems with this, but then, okay, this is now outside of the screen. So what we see here, that's annoying. So this is hexane water mixture, and the hexane is like this 2-bead stick thing, and then the water is represented just as balls in the coarse grain model. And then when we run the simulation, then we see that they are demixing or phase separating, which is what we expect from an oil-water mixture. Like the system where we want to insert our molecules and then having them have a preference for this in comparison to the individual solvents. And then the details here with this free energy calculations, you can read through this yourself. And then we run, in this case, an example simulation for one of the coarse-grained molecules, and then get this free energy difference, which is called delta delta G here. And we, like, this is the property which we want to optimize for in the end. And now start with, or yeah, introduce the optimization. We first enumerate our chemical space. So in this case, simple, this chemical space is relatively restricted. For example, we don't have any charged molecules. Yeah, but for the demonstration, we want to keep it not too complex. And then this figure shows the coarse-grained beads from our transferable coarse-grained force fields, and we use to construct our chemical space. So yeah, since we, for example, exclude charged molecules or charged beads, this is not like the full chemical space, but we use this to make it, or to keep it accessible. And then we use simple combinatorics to generate molecules. This is a super important thing. We restrict ourselves to molecules with only 2 coarse-grained beads. So they are relatively small, but this, again, this reduces like the complexity. But this works also for larger molecules. And then we have this hierarchy with 2 levels. And this figure shows that the molecule on top with beads which are called K4, whatever this means, this maps to like all these molecules on the higher resolution, and this is like keys what we want to use for the optimization. And then there are some pre-computed values that you don't have to run all the simulations for this low resolution model. But before we actually start the optimization, we, because molecules are discrete, want to transform them into numerical encoding space. And yeah, I skipped the details here. So we use a regularized autoencoder, and when we do this, then this is how our encoding space looks like. So we see now all our molecules scattered across this to the space, and in general, the structure of this. So we want to use this space for our optimization in the next step. A structure which we have in the space is quite important for the optimization. So if these points would be scattered randomly, then this wouldn't help us with the optimization. So the idea is to have reasonably structured space here, which is not straightforward. So we need to have some information about like molecules which we use here, and the input information which we put in should somehow be related to the properties get from our simulation in the environment. So this is like a relatively simple way how it is done here. So we just assume that there are, I think, 4 different classes of beat types, and then this is all information which we put in. So this could be definitely improved. But for this example, it's fine. And then we see, for example, that, I don't know, this is like a molecule which has the beat called NP6, and it's neighboring to a beat molecule with a beat which is N5 and P5. So they are relatively similar, and this is what we want to have, because this helps us in the optimization, that similar molecules are close to each other. And so the idea is to now use this base for our molecular optimization, and we use the delta learning approach, which was mentioned in the presentation. So we have the free energy from the low and then learn the difference to get our high resolution, and then this is the way how we use the lower resolution model, hierarchical optimization. And when we run this, I don't know who actually got to this point, because this is like the most expensive suit, because we are running multiple simulations, and this is based on like the Bayesian optimization, which I don't go into the detail because we'll hear about this tomorrow. I could still mention. So in the beginning here we construct, for example, we construct this zero-gate model, which we then fit, and then this gives us a mean prediction and some uncertainty estimation, and it is important for the Bayesian optimization. And what this delta learning, which I mentioned, is implemented in a way. So first we subtract the low resolution prior, and then we like learn our surrogate model only on the difference, and then we added like the in, and this is how we do this delta learning. And then we run this Bayesian optimization loop for a while, and then so I had 20 steps. I think in the notebook you had like 10 steps set up, and then we get like these molecules, and then so in my case, so the molecules you get depend on the initial conditions, so this is kind of random. In the run I have here, I got like this molecule C1P, and so I didn't talk about the properties of the beat types which we have here, but you might have thought about this, like C is apolar beats and P represents polar beats, and from this set of beat types which we used for our simple model, actually a molecule with a very apolar beat and a very polar beat, which is kind of what we would have expected. And so a simple example of the coarse-grained optimization, and we can now derive like chemical design rules based on this. I mean, in this case, super simple, but for for larger molecules, they are maybe more interesting. And then, so before I talk about the key takeaways, I think I showed the optional results. We can smaller again. So this is now our latent space, and then the estimation from our surrogate model, and then so yellow is like better estimates, and then we can see like there are neighborhoods where we expect to have better molecules, like the yellow regions, and then there are molecules which are like supposed to perform quite bad related to our target property, and we can also visualize during the optimization, and then it's not changing much because we have this low resolution prior incorporated, but then dating a little bit because we are doing this delta learning. And then based on the results from this optimization, we can derive some promising molecule structures. Like besides the one which we actually evaluated, we can also obtain from kind of similar molecules because they are neighboring molecules in our latent space representation. So this is shown here because in the end we are still interested in atomistic structures. What I have here is like, let's say, to reconstruct atomistic structures based on the hydrophobicity of the beads and some atomistic fragments. So this is not an exhaustive list, but this is a way to get like atomistic structures based on the coarse-grained beads, which we obtained from our optimization. And now I scroll back to the key takeaways from this tutorial. So that the first thing is that coarse graining models can be used to kind of compress chemical space, and then when we do a latent space of the discrete molecules, we can use this encoding for the optimization. And then this hierarchical approach also helps to make the optimization. And in general, Bayesian optimization is a good approach to optimize so-called black box function, like where we have no idea about the shape of our optimization landscape. And with this, at the end, if you don't have any other questions.